broaden our thinking, and transform of what we are about to study. Lord, we bring before you these prayers. We ask all of this in God's name. Amen.
I invite Ms. R. Pricey Matilda, Assistant Professor, to welcome you all.
A pleasant morning to everyone. I feel great to welcome you all to this national level webinar on emerging trends in the field of material science 2021. First of all, I thank the Almighty God to be here to give the welcome address. Not everybody can be famous, but everybody can be great because greatness is determined by service. I'm glad to cordially welcome our College Secretary, Reverend Mother C. Noel Ronnie, FSAG, on this occasion. Welcome you, Mother. Some are born great, some achieve greatness, some get it as a graduation gift. I have immense joy and pleasure to welcome our principal, Reverend Sister Dr. E. Grita Sumangali, FSAG, who have supported us to spread the light of true knowledge. Welcome you, Sister. It is so much easier to honor the leaders who are honorable. I heartily welcome our Vice Principal, Reverend Sister A. John, guide and encourage in the proper way. Welcome you, Sister. An honor is a special award that's given to someone, usually because they have done something good or they are greatly respected. It is my privilege to welcome such a noble personalities as our chief guests, Dr. K. Seduraman, Associate Professor, Department of Material Science, Central University of Tamil Nadu, Thiruvarur. Dr. S. K. Das, Head and Professor, School of Physics, Gangadhar Meher University, Sambalpur, Odisha. Dr. S. Bhuma Devi, DST Women Scientist Department of Physics, National Institute of Technology, Tiruchirappalli. We welcome all resource persons. Those who educate children well are more to be honored than parents. For these only life, those are the heart of living well. I extend my warm welcome to all the staff members for taking a keen part in this program and making it successful. I would like to welcome all the students who are the integral part of this program. I request all for your kind cooperation throughout the program and making it a grand success. Once again, I welcome you all. Thank you.
Success is liking yourself, liking what you do, and liking how you do it. I request Reverend Dr. E. Grita Sumangali, FSAG Principal, to inaugurate the webinar.
Thank you for inviting me. Respected Reverend Mother C. Noel Rami, Secretary, Reverend Sister A. John Diana, Vice Principal, Dr. K. Seduraman, Associate Professor, Department of Material Science, Central University of Tamil Nadu, Thiruvarur, Ms. K. Devi, Head and Convener of this national level webinar, Sri Sweta, Association Organizing President, members of the Organizing Committee, participants from various colleges, and dear students, happy morning to all of you. It gives immense pleasure to share with you my wishes and appreciation at the event that the Department of Physics is organizing national level webinar on emerging trends in material science today. This webinar is focusing on the high impact topic of material science, advanced materials and processing. Material science of today is the innovation of tomorrow. The conference brings together the leading researchers to share and engage in high-level discussion on the trends in materials. Participants may get a wide range of networking opportunity to meet peers and to have discussions with them, working on solutions to some of the key issues facing material scientists today. Industrial breakthroughs commonly go hand in hand with new materials development. Rapid advancement in material science further allow accelerating research and experimentation while enhancing material sustainability, lightweightening, monomolecular, and programmable qualities. In turn, early adapters of these material industry trends in aerospace, automotive, manufacturing, energy, logistics, and packaging reap the benefits of emerging innovation. It's worth identifying and implementing materials innovations, considering the wide range applications of new materials in industrial, commercial, and also for household products. In order to comply with the requirements of certain industrial use cases, novel materials currently in development possess application-specific characteristics. Advancements in material science allow for creating smart materials with programmable properties so that they behave or respond to stimuli for external factors. Emerging companies work to design materials and products with diverse qualities from thermo, electro, and photochromism to photoelectricity, shape memory, self-healing, and phase-changing attributes, among other characteristics. I'm very sure that national level webinar will throw a light on emerging trends in material science research. The material industry trends certainly help the researcher in identifying new opportunities and emerging technologies to implement novel materials and smart materials into business. On this special occasion, I have the pleasure of appreciating the convener, organizing president, members of the organizing committee, and the students of the Department of Physics for having taken a lot of effort to bring eminent resource persons from various reputed institutions to have effective deliberation. This department has a record of organizing international conferences and producing good researchers with academic competence at its very young age of existence. Hope and wishing you a very productive sessions. All the best. God be with you.
Thank you, sister. I call upon Ms. S. Nisha Priya, second MSc Physics, to introduce our resource person.
Thank you, Niveta. Happy morning, everyone. It's been a long day. It's been a long time waiting. It's been a honor to have been invited to introduce our eminent speaker. Now, I'm going to do a short story to introduce someone who's known to everyone. And there with me, it is going to be short. If you don't like something, then change it, take action, and don't complain. All before, at initials, he has constructed his bachelor's and master's cum philosophy in physics at Bharathidasan University, Tiruchi. By grouping of years, he has doctorate in physics at Anna University by the year 28. His galvanized efforts resembled in the form of academic experiences as a lecturer in the year 23 at SKSS College of Arts and Science, Tamil Nadu. Served in place of assistant professor in the year 29 at Concord University, Seoul, South Korea. Also in the
Are
year
you a finance
2010, he has
professional
encouraged the
or an
roused
accounting
and young
student?
minds at Madurai Kamaraj
So
University.
sure of your
On
career
credit of
options.
his hard work and interest, he extends his career as an associate professor in the year 2020 at Central University of Tamil Nadu, Tiruvarur. During his PhD work, he has done poly research work in many associations and various laboratories. And also, he has an extensive experiences on small nuclear semiconductors and applications like P-type and N-type organic FET, crystal growth using organic materials for nonlinear optical applications. Here, his principal research interest grabs my work to learn for you about his honors and awards as well. He has 18 years of experiences in material science and electrical engineering. His phase as a researcher who got a Japanese government fellowship in Department of Electrical Engineering, Aichi Institute of Technology at Kyoto, Japan. By extending the year 2015, he climbed the Raman U.S. postdoctoral fellowship in Mint at University of Alabama, USA. As an appreciation of his committable work, he has guided 8 scholars and still interested to guide the young streams. In all to excite, he has presented 85 international journals and also organized quartz conferences. All about the session, and it is now my pleasure to welcome on behalf of all the younger and hunger minds in the session. The man you are waiting for is Mr. Dr. K. Seduraman, Associate Professor, Central University of Tamil Nadu, Tiruvarur. We welcome you, sir.
Thank you for the nice introduction. Can I start now? Yeah.
Yes, sir.
Yeah. Okay. Thank you for your nice introduction. Very good morning to one and all. Mobile phone with the OLED display, 90 to 95% of displays in mobile phones are prepared by organic light emitting displays. So in advertisements, majority of the mobile advertisements, people used to show that all AMOLED displays. And then really what is AMOLED? Active matrix organic light emitting diode structure displays. And in detail, we will see that later, really how it is influencing our lighting applications and displays applications in our day-to-day day life. So first part is I'm going to say discuss about organic solar cells, how that organic solar cell is different from other traditional inorganic based solar cells. So before going to see in detail about the devices, the first thing is you should know that what is organic electronics. Organic electronics, generally speaking, it is a multidisciplinary science and technology that is related to a class of organic material, both single molecules and polymers. So used to fabricate a device, organic electronic devices. So our aim is here using organic electronics is ultra low cost. The fabrication cost is low compared to traditional. So lightweight because you prepare your device on even plastic or simple substrates, simple even on papers also. So that what happened that a lightweight device compared to the tough inorganic based electronic devices. And and also we can say it is a flexible electronic devices for the displays. And then maybe you may aware that recently Samsung introduced that flexible mobile displays on the mobile phone. So organic circuits and memories, or we can print that, we can prepare that memory devices and circuits on anywhere and placed so even on paper, plastic, anywhere because of organic devices. We used to prepare it by at room temperature. So that is the reason organic electronics cost-wise is very low compared to that of traditional inorganic based electronic devices. So and also we can synthesize organic materials so that we are having unlimited diversity of synthetic organic chemistry. It allows tailoring of organic molecules with respect to the optoelectronic properties. So we never say that we cannot replace the traditional silicon-based electronic devices, traditional inorganic-based electronic devices in some cases due to that of lower mobility in organic material compared to that of a traditional inorganic material. So that's why that organic electronics are playing definitely. So nowadays, slightly changing that some of the low power electronic devices are completely fabricated by organic materials. I told you that in the beginning, organic light emitting diodes nowadays completely prepared by organic material, using organic material. Organic semiconductors, so what? It is unlike a inorganic based semiconductor that are crystalline with a band like a charge transport, but organic semiconductors are amorphous, polycrystalline in which the charge transport occur through hopping of charges between delocalized pi molecular orbitals. So organic material definitely composed of hydrogen, carbon, and oxygen. So really what happened in a conjugated pi-electron system formed by a piece orbital of sp2 hybridized C atoms in molecules. So that the lowest electronic excitation of a conjugated molecule or pi star transition with an energy gap typically between 1.5 and 3 electron volt so which is leading to a light absorption or emission in the visible spectral range. So organic chemistry offers a wide range of possibility to tune the optoelectronic properties of organic semiconducting material. So organic semiconductor, generally we can classify that organic material into small molecule and long chain polymers. A small molecule, you see that by sigma bonds and sp2 hybridized orbitals. So these pi bond this is a delocalized pi electrons pi system. So it helps to transport a charge carrier through this small molecule, and that same like long chain polymers. So pi bond, pi conjugated system is highly uh, useful to allow that. I mean, charge carrier generally uh, passing through the pi conjugated orbitals in an easy way. So that is the reason organic semiconductors, small molecule or long chain polymers conducting. It's a small molecule semiconductor, organic semiconductor. This is a phthalocyanine, general molecular structure of a phthalocyanine. This is also a small molecule small molecule organic semiconductor. So this one is a long chain polymer, so poly 3-hexaphene. And then when the field of organic electronics is just moving, that I used to put whenever I am taking the seminar and giving a talk on the organic electronic devices. This is a very good story that milestone in the development of organic electronics, an accidental discovery, how how it happened. So at the beginning of 1977, Shiragawa was Professor Shiragawa. He's from Shukuba, University of Shukuba in Japan. He was studying that polymerization of acetylene. So in his reaction vessel, that polyacetylene appeared in the form of unremarkable black powder. So on one occasion, a visiting researcher accidentally added 1,000 times more catalyst so that so the film is found on the surface of the liquid in the vessels. So that if the film is I mean, that silvery film is uh, whether it will conduct electricity or not, that's the question mark. So that they have checked it that they are conducting electricity. This one is the first conducting polymer reported in the literature. So first conducting polymer, that this is a polyacetylene. Polyacetylene was doped with, this is a uh, halogen, so that doping polyacetylene with the halogen, so that increasing its electricity. That before doping, that you see that electrical conductivity. So electrical conductivity of the 38 Siemens per centimeter. That is almost 10 orders of magnitude increase in conductivity in the conducting polymers. So with a small doping. So this one was published in the year 1977 by three scientists, Shiragawa and McDermott and Alan Heger. So for this, after that, after the invention of a conducting polymer, and so there is a huge development and discoveries of different conducting polymers. So that for that reason, for their contributions to the invention of conducting polymer, that all three great scientists awarded the Nobel Prize in Chemistry in the year 2000. He is a Professor Alan Heger from the University of California at Santa Barbara, and he is a Professor Hideki Shiragawa from the University of Shukuba, Japan, and then Alan McDermott from the University of Pennsylvania. So after the development of that conducting polymers and organic small molecule semiconductor, so there is a huge development using those organic semiconducting material to fabricate different electronic devices, so like a different devices like organic filter transistors, displays like organic light emitting diodes, so radio frequency identification tags, and then solar cells and organic memories. So different applications, and then different applications of using organic semiconductors are there. Then we are going to see today is organic solar cells and organic light emitting diodes in detail, how that organic solar cells are working. So that my first part is organic electronic devices, organic solar cells. I told you that organic material we can classify it into two different types. One is organic small molecule, and another is organic long chain polymers. Organic small molecules are not dissolvable in solvents, any solvents. So that's why we generally organic small molecule thin layers, thin films prepared by using a thermal evaporation technique. But organic long chain polymers generally used to dissolve in solvents and then easily preparing a solvent, and then they used to prepare that layer, thin layer of organic polymer materials by simple solution technique like a spin coating and then dark casting, etc. So organic solar cells, so before going to see in detail about solar cells generally, so why we are interested in solar cells and ever increasing energy demands of the population. Of course, nowadays that we are always looking for the renewable energy resources. So that definitely we cannot rely on that for traditional fossil fuels. Uh, so that and also people's are very difficult to control the climate. I mean pollutions that I mean pollutions created from that burning of the fossil fuels in different uh, power stations. So that always we are looking for alternative energy, that renewable energy. So people's always thinking that abundant energy available in the earth is solar energy. So we need a 30 terawatt of power, but sun is gives that almost 1,20,000 terawatt of power. That solar cells are safe. That sun shines when we need energy the most. So using this energy in a very uh, good way to convert it into electrical energy by using solar cells. And then generally solar energy that sun gives almost 3 into 10 to the power of 10 to 24 joule per year of energy. It is about 10,000 times more than the global population consumptions. So suppose if we uh, can cover about 0.1 percentage of our total Earth area with the solar cells, which have a 10% efficiency, that energy produced will satisfy our our current demand. So that solar cell is a general introduction about that solar cells, even for some young people and researchers may be useful. So basic idea of a solar cell is to convert light energy into electrical energy. Solar cell is a very large diode, so it supplies a current, voltage and current to a resistive load. Solar cells are silent, no maintenance are required, no fuels and no emissions from solar cells. So history of that general solar cells, it was first that photovoltaic effect was discovered by Edmund Becquerel in the year 1839. So, first silicon solar cells was fabricated in a Bell laboratory by Chapin, Fuller, and Pearsons. That they achieved the power conversion efficiency of 6%. So, organic based solar cells. So, they started organic solar cells fabrication by the year 1986. So, in the inorganic based solar cells, they achieved the power conversion efficiency of 40% in the spectral laboratory in the year 2007. So up to now, that recently a company in Japan, they have achieved the organic based solar cells efficiency of about 25%. So maybe we will see it later. Uh, so this is the general basic of that solar cell, photovoltaic cells and modules and systems. Solar cells is the basic building blocks of the solar PV. So this is a solar cells. Cells are connected together in series and encapsulated into modules. How you see that these cells are connected together in series and encapsulated into modules. So model can be used singly or connected in parallel series into an array with a large current and voltage output. So this is a photovoltaic array integrated generation generally used to see that a silicon-based solar cell, a large and non-flexible with a high manufacturing cost. So silicon-based solar cells are still dominate in the market, almost 85% due to the high efficiency. Second generations of silicon-based solar cells. So for silicon, nanocrystalline silicon, cadmium telluride based solar cells, and third generation is a new generation, next generation solar cells. Still in the research phase, include a wide range of potential solar innovations, including polymer solar cells and nanocrystalline solar cells, dye-sensitized solar cells, and perovskite solar cells. So organic solar cells are based on organic semiconductors. Organic semiconductors have attracted much attention. Generally, the thickness of the active layer of organic solar cell is typically only 100 nanometer thin, which is about 1,000 times thinner than for crystalline silicon solar cells. The low material consumption per area and the easy processing of organic semiconductor offer a huge potential for low-cost, large area solar cells. This is a organic organic polymer solar cell fabricated on a flexible substrate. So, organic small molecule based solar cells prepared by vacuum deposition. I told you that organic small molecules are not dissolvable in solvents. That's why all the material, all the thin layers prepared by vacuum deposition. Polymer and polymer composites based solar cells are prepared by solution and low temperature processing. Dye-sensitized is an electrochemical cells and it is used to prepare isolation processing. So all these cells face more or less the same challenges. So our ultimate aim is to enhance the power conversion efficiency of the solar cell, fabricated solar cell. So and also that increase the stability of the solar cells, and then how it is stable in air. That is a very important thing. And so that for commercial applications, we need a air stability. So increase the stability of organic solar cells, and then develop a technology for large area. So for a large area development, so we need a special technology. So and also low mobility of the charge carriers. So in the case of silicon and then polymer cells. So in the case of crystalline silicon, you see that probability is 1,000 centimeters per second, but polymer, you see that probability is 0.1 centimeters per volt seconds. So low mobility of charge carrier in organic waste materials. That's one of the important point to always keep in our mind to enhance the how we enhance the mobility of the charge carrier in organic material, organic semiconductors. Difficult to obtain a low band gap material by synthesizing organic material. It's very difficult to obtain a low band gap organic material for organic solar cell applications. So, for organic solar cell point of view, that organic solar cells need a high absorption coefficient, and definitely low cost, lightweight and large area. We can fabricate a solar cell on a flexible substrate. So color, we can produce the color, different color of the solar cells, and also it is a semi-transparency. Semi-transparency we will get by synthesizing a material. So with the different more functional groups and insensitivity to temperature. And then solution processing means they can be printed on a substrate rather than requiring a lithography. So once you want to prepare the device by going for a lithography, again the production cost is very high. Lithography is the sophisticated instruments. We need to use those instruments in a clean room, as a clean room only. So again, so that we should, so without doing a lithography, that how we are printing that solution processing. And by using solution processing technique, how we can prepare the devices by simple printing technique. It is also very important, but we can print that organic solar cells by simple printing technique, and also ability to control HOMO energy levels. Then you will see it. So reason for organic solar cells. So production cost, efficiency somehow lesser than that of traditional inorganic based solar cells, but the production cost is you see that really less. So that compared to that of inorganic based solar cell, production cost of organic solar cells are very less. So that's why that people's always thinking about that organic solar cells. So methods of preparation, different methods are there. Like first one is a printing, roll to roll manufacturing. You see that it's roll to roll manufacturing is nothing but that printing our papers, our daily magazines, papers, newspapers are printed uh, by simple printing technique. In the same way, one can print that solar cell structure, three-layer, two-layer, three-layer structure by simple roll manufacturing technique, same like a printing technique, and screen printing and stamping and spraying and that. But spin coating is the majority of the people in R&D research and development scale and laboratories using a spin coating technique. Once your material is soluble in organic solvent, you can go for a spin coating technique. So if it is not dissolvable in organic solvents, then definitely you can go for the vaporization technique. So spraying, by spray also that people used to prepare that organic solar cell, different stages used to play, and then finally they prepare a contact by using evaporation technique, either aluminum or calcium contact by evaporation technique. So organic solar cell material choice is very important here. So material choice is a critical. So one should always remember that absorption spectrum. So then also energy levels of the, HOMO-LUMO energy levels of organic material, and the electron transport layer and hole transport layer of that organic solar cells are very important. So always we should keep in our mind about absorption spectrum, energy level of organic material, and then electron transport and hole transport layer. And then I already told you that limits of a low synthesizing of a low band gap material is very difficult. So that because the limits of low band gap polymers are having a low absorption coefficient. So we need a high absorption coefficient for an efficient organic solar cell. So and also low carrier mobility and solubility is very difficult. So that and low voltage. These are all some limits of low band gap polymers. General energy levels and the diagram of organic solar cells, and then generally ITO and then aluminum cathodes are there. So on the surface of ITO, then we used to prepare different layers of organic semiconductor on the surface of organic semiconductor electrode. So aluminum electrode used to deposit. This is the energy level diagram. You see that HOMO highest occupied molecular orbital and lowest unoccupied molecular orbitals of organic material, organic semiconductors. So fabricated here, you see how that HOMO level is matches with the ITO energy level work function, how that LUMO level is matches with the work function of aluminum electrode. This is aluminum electrode work function. This is ITO electrode work function. So what happened that light is incident on the material, light absorption takes place, then exciton generated, and then electrons are excited to that LUMO level, and then excited electrons are travel towards to the aluminum electrode, and then holes are created, and created holes are travel towards to the ITO anode. So that circuit and current is generated. So the current is in the external circuit. Current is connected in the external circuit. So this is a work function. This is an electron affinity, and then ionization potential. So it is very important to match the work function of electrode. You may deposit a different electrode, but they should match with the LUMO level of your organic material. Then you can easily and then efficient way you can harvest that electron and the electrode. So that, and also it is very important to match that HOMO level of your semiconductor with the ITO. So then you can harvest that charge carrier. You can get more number of charge carriers without any destruction. So this is an excitons, and then binding energy in organics is about 0.4 electron volt. Exciton binding energy in organic semiconductors generally large compared to that of silicon. The built-in electric fields are usually not high enough to dissociate excitons directly. In organic semiconductors, the built-in electric field generally are not usually not high enough to dissociate the exciton directly. So that in organic semiconductors, in organic solar cells, the dissociation, exciton generated, how where it is dissociated. So dissociation site is in organic semiconductors are electrode interface, crystal defects and impurities. So the diffusion length is about 100 nanometer thin layers. So 100 nanometer thin layer is needed for the diffusion. Process so that it must be dissociated to get a free charge carrier. So these are all the different device architecture used in organic solar cells, and single layer organic solar cell and bilayer heterojunction organic solar cells. Single layer between the two electrodes, aluminum and ITO electrodes, and organic thin film, organic semiconductor thin film fabricator that generally used to call it as a single layer organic solar cells. So in the case of bilayer heterojunctions, we are having a donor organic semiconductor and acceptor organic semiconductor between the two electrodes. So generally used to call it as a bilayer heterojunction structure. A bulk heterojunction. Bulk heterojunction means that if you are preparing some polymer composite, it is dissolvable in solvents. You prepare that polymer composite between aluminum and ITO, then generally used to call it as a bulk heterojunction. This is a tandem structure. So stacking of that solar cells one by one, so that this is a bottom device and a top device. Tandem structure. So generally, uh, generally dispersed dispersed are bulk heterojunctions. So dispersed or bulk heterojunction means the exciton dissociation. So exciton dissociation in most effective at the interface in heterojunction cells. So dispersed or bulk heterojunction. So exciton dissociation is very effective at the interface. Exciton should be formed within the diffusion length of the interface. So if the length of the layer is very high, mean that diffusion is very difficult. So that since typical diffusion length are in the range of 10 nanometer, so this limits the effective light harvesting layer. So most organic semiconductors, the film thickness should be more than 100 nanometer in order to absorb most of the light incident on the surface of the organic semiconductor. So that thicker film layer increase the light absorption, but only a small fraction of the excitons will reach the interface and dissociate and the charge carriers. So we are facing a dissociation problem in most of the uh, thick layers that are fabricated in solar cells. So if you prepare a very good thick layer means more than 100 nanometer layer, it will definitely absorb a very good light, but it's very difficult to dissociation takes place. In that diffusion is very big problem in that type of a layer. So that problem can overcome by just blending of a donor acceptor. Suppose if you are using a traditional heterojunction, so traditional heterojunction, I told you that this is this layer. So if of the traditional traditional heterojunctions, so exciton is generated diffusion towards to that of at the interface. Generally, dissociation is happen at the interface. If it is more than 100 nanometer, then reaching that at the exciton at the interface is very less, so that it will reduce the power conversion efficiency. That's the reason, so that people now going for the concept of a dispersion or a bulk heterojunction concept. This is a bulk or a dispersed heterojunction structure. That it is clear that a control of morphology in uh, control of morphology in a dispersed heterojunction devices is a critical point. So degree of you see that phase segregation, phase separations, and domain size depend on the solvent size. This type of phase segregations and domain size is depends on the solvent size, speed of evaporation, solubility, visibility of the donor acceptor. So we are just preparing a blend, and then just blend is the depositor in between ITO and aluminum. That blend is making some domains and phase separation. So each domain is each part, the domain size, each domain boundaries act as a dissociation site for the excitons. So that efficient way that we can dissociate the exciton by using a bulk heterojunction concept. one strategy towards increasing control is the covalent link and donor acceptor. And so these are all that you see that a planar heterojunctions formed between the thin films of donor acceptor material. So that you see here uh, dissociation of a charge carrier at the interface. So once a charge carrier is dissociated, it is a charge carrier now moving towards the concerned electrodes. But this is a bulk heterojunction. So bulk heterojunction, so optimal bulk heterojunction where there is a complete phase separation. You see the phase separation of a donor acceptor to one side and acceptor to the other side of the device. So, so that for this, then easily excitons and you see that easily exciton dissociation of the interface of the gray domain. So easily it is dissociated and connected in a concerned electrode. So this is our desired choice, optimal bulk heterojunction choice, a planar junction. So we are having a diffusion problem. So that but in the case of this is a non-ideal bulk heterojection because the controlling of morphology is very important here. You see that isolated domain here. This type of domain will generate. I mean, excitons are dissociated in that here at the interface, but it cannot go to that at the end other part of the electrode, so that so it is in no ways meaningful this type of isolated domains. So it may reduce the charge carrier separation in the bulk heterojunction concept. So that optimizing the morphology is a very important bulk heterojunction concept. So different morphology of heterojunctions. So two-layer structure of fullerene and polymer chains. So this is a fullerene. So fullerene means C60. So that and the polymer chain. So they are mixing two-layer structure of fullerene and polymer chain, and they are creating so for a molecular heterojunction. Different morphology of heterojunction cells and disposed ones. And then you see that it's not a separate layer. Fullerene disposed in between that polymer chain. So this used to call it as a disposed heterojunction. So fullerene with the polymer chain attached. So polymer long chains are attached at the end of the fullerene. So this is another structure. So this is a self-assembled layer structure of a double cable, so that easily charge carrier separation of the takes place. So these are all some of the different morphology for heterojunction cells. So bulk heterogeneity generally people in the beginning of having inventing the bulk heterogeneity concept. And, scientists or created and scientists are prepared that Polytheics, say, paraffin and PCB based material for the bulk heterojunction. So and then for this type of bulk heterojunctions, they achieved the power conversion efficiency up to 5%. So earlier of that, I mean, almost in 2000 to 2010, they have developed a different material. This is the first material they tried for the bulk heterojunction concept, PC3, P3H2 and PCB. They achieved somehow that efficiency near to the top 5, but it's very difficult to enhance the efficiency so that they synthesize a different type of material. So that so different materials with different properties. So this is again that they are changing that morphology. So before annealing, so they prepared that P3H2 PCBM. So before annealing, it is how that materials are segregated on the surface of the substrate. So after that annealing, you see that how that rearrangement of P3H2 and PCBM. So once it is rearranged, it means then you see that we are having a beautiful interfaces. So that at the interface, the exciton dissociation takes place, and then we are trying to enhance the power conversion efficiency by using this type of additional and additional either doing annealing or doing annealing at room temperature and vacuum, etc. So packing of conjugated polymers with the fullerene based molecule. So this is another concept that how that they are preparing that conjugated polymers. These are long chain polymers with the fullerene. so that they prepared. See that fullerene is attached to the polymer like this, and then how the fullerene is attached to the polymer in two directions. Then how they are preparing layer one, layer two concept. And then the ultimate aim is to get the maximum power conversion efficiency. So after annealing there, what happened to that of morphology that you see that before annealing, that after annealing that some phase separation is there, some um, changing the salinity and then aggregations of P3HD, PCBM in NFS. This will help to enhance the power conversion efficiency. This is additive concept, additive for improved efficiency from bulk heterojunction solar cells. Then this work was reported in the year 2018. So the synthesized PCBT PCBDT and BT-PCB. It's a BT. BT is a kind of polymer, long chain polymers they prepared, and then they have used that 1,8 diiodo octane as a processing additives. That by using these processing additives, so the efficiency of a bulk heterojunction solar cell was improved from 3.4 to the 5.1 percentage. So by using this additive, so it is simply used to segregate that the molecules, so that by using this segregation, they are achieving the very good exciton dissociations at the interface, so that they will enhance the power conversion efficiency. That's another structure, tandem structure. So why we are people are interested in tandem like a structure means that absorbing a major part of solar spectrum, hence to increase the efficiency of the device by increasing so that the electric current. So this is a bottom cell and top cell. So a stacking of the solar cells. So generally used to call it as a tandem structure. So on the surface of ITU, they prepared a first cell, and then again they prepared another cell. This is a bottom cell and top cells, and finally they prepared an aluminum electrode. So this approach is to fabricate a PN, PIN, or any other diode structure with a different band gap semiconductor. Why they are choosing this tandem-like structure you see here, so that cell 1 is absorbing the first part of the solar spectrum, and cell 2 is absorbing second part and then third part. So ultimate aim is to absorb the maximum that solar spectrum. So that is the reason cell was one at the front is fabricated with a wide bandgap material to convert high energy photons from blue end, and then cell 3 is at the back is fabricated with a narrow bandgap to convert the low energy photons from the infrared end. So they are capturing the more solar energy. Then once they are capturing the more solar energy means then they will convert it into and an efficient way. So that's why they are doing it in a stacking structure. That this is called as a tandem structure. So inorganic, some people using that inorganic interlayers for organic photovoltaic devices, and then electron transporting and hole blocking, and then reduce the charge recombination, organic optical spacer, etc. Required properties for OPV application is optically transparent, and then the inorganic interlay is optically transparent, solution processable, chemically stable, room temperature processable, and the non-vacuum process. Because once you go for a vacuum process, again the fabrication cost is very difficult. We need to get high vacuum. So that is the reason that interlayer concepts introduced, but by using this type of interlayer concept, then they are trying to improve the efficient charge connections near to the tough electrode. That's why they're using some type of inorganic interlayers in organic photovoltaic devices. So that generally organic for solar cells are 5 critical steps in organic photovoltaics. First one is photon capture. So next is exciton diffusion. So I told in the beginning, exciton diffusion is happened at the interface. So within 5 to 5 nanometer regions, charge separation is the next step, and the fourth step is charge transport, and then fifth one is a charge collection at the electrons. And then 5 critical steps in organic photovoltaics, and then how do charge carriers separate in an organic heterojunctions? And I told that anode and cathode, in between anode and cathode, we are having a bilayer, so donor and acceptor layer, organic layer, so that in how that bilayer in bilayer exciton is dissociated. We will see it. So again, that process that important steps is absorption, exciton diffusion, and charge transfer and the charge collections. The horizontal lines to the left to right simply indicates that Fermi energy levels of the cathode and the anode contacts with that organic homologular of the organic donor and the acceptor material. So first one is that simply that absorption, so light absorption, so that how that light absorption is takes place in that in the organic solar cells, so that simply that optical absorption length here on the donor layer is about 1000 angstrom. So simply this using this is the efficiency of absorption. Absorption efficiency of light within the active region of a solar cell. It is depends on that layer. So and next is exciton diffusion. So after absorbing that material at the surface, how it is diffusing exciton is formed, and how it is diffusing the exciton near to that of that interface. Because I, uh, I told you earlier that the exciton dissociation is happen at the interface only. So that so once exciton is generated and then it is diffused and going near to the interface of a donor acceptor. So generally exciton diffusion length is and then 50 angstrom only. So that this one gives the exciton diffusion efficiency, how it is dissociate to dissociate the site. Another is exciton dissociation. So once it is that reaching the interface of a donor acceptor, how it is dissociated, so that charge carriers, so that electrons are dissociated and move to the low model of the another material, and then holes are moving towards to the other electron. So this is a donor acceptor interface. In at the interface diffusion, electron, I mean at the interface exciton diffusion dissociation is takes place. The electrons are moving towards to that of that aluminum electrode, and then holes are moving towards to that of ITO electrode. So charge collection. So after dissociation, electron collected at the cathode and the holes are collected at the anode. So all steps are important in organic solar cells. And then if there is anything happens or anything if not efficient, then definitely will not get a maximum power conversion efficiency. So are these some parameters how we are calculating in organic solar cells? And then quantum efficiency is simply refers to the percentage of photons that are converted to electric current when the cell is operated under short circuit conditions. Then generally quantum efficiency measured internally and external quantum efficiency. Then internal quantum efficiency is the fraction of absorbed photon that are converted to electric current. So that external is a fraction of incident photons that are converted into electrical current. So and also we are just after measuring that. So these are some of the important parameters we are extracting out from the JV characteristics. So fill factor, and then short circuit current, and then this is a short circuit current, and then FF is a fill factor, and then JPH is a photocurrent, and then VOC is open circuit voltage. Is open circuit voltage. Generally, after fabricating solar cells, then we used to measure that, do the measurement in dark and as well as the illumination, sun illumination conditions. So, and then finally calculating the power conversion efficiency using all the parameters, all the factors, so one can get the power conversion efficiency. So the most effective strategies include structure, so thereby increasing the diffusion length and absorption coefficient, so that implying a material with long range order, thereby increasing the diffusion length. So implying a bulk or mixed heterojunction between a donor and acceptor material to increase the um, absorption without decreasing the diffusion length. So, mixed heterojunction, bulk heterojunction is a very good for the without sacrificing that absorption with the decreasing diffusion length, so that we will get a very good power conversion efficiency in this concept. So employing a light wrapping schemes or multi-electron, tandem stacking style to increase the optical path length within the thin film, thereby increasing the absorption property of the solar cell. These are all the effective strategies to fabricate an organic solar cells. So this is the structure. Then already I told you that this is a bilayer structure. So small molecule thin film donor acceptor, and then between ITO and anode, ITO and the cathode. So this is the bulk heterojunction. Donor acceptor blend is prepared in between cathode and ITO. This is the structure of organic solar cells. So these are some of the structures I mentioned here, the two-layer structure, and then bulk double heterojunctions, a double heterojunction acceptor donor, and electron blocking layer. Another is preparing a donor acceptor bulk heterojunction, mixed heterojunction layer. So this is called planar mixed heterojunction, because the donor after preparing acceptor we are having a blend layer. So this is a planar mixed heterojunction. This is a tandem structure, the stacking of the solar cells, so that the same structure repeated and on the surface of the one to other. So these are some organic structure used for the fabrication of organic solar cells. So this is the first work reported in literature that using phthalocyanine and perylene by C.W. Tang and then Eastman Product Company. That this work was published in the year 1986. They achieved a power conversion efficiency of 1%. So using this phthalocyanine donor and perylene acceptor for a small molecule. Both are small molecule semiconductor. Both layers are prepared by thermal evaporation technique and under high vacuum condition. So bulk heterojunction prepared by the Yan group as well as the Alan Heger group. And so they published a paper in the year 2007 and 2005 using acceptor, small molecule, and then they mixing and these two, and then preparing a blend, a donor acceptor blend, and then prepared the thin layer between the two electrodes. This work, they achieved the power conversion efficiency of 6%, 5 and 6%. So these are all some literature I put here. Then, so this is a recent work, the highest power conversion prepared by long chain polymers. So halogen-free solution process. So if they achieve the power conversion efficiency, they synthesize the new material and they use those new material. So without halogen-free solution process, so that they achieve the power conversion efficiency of 16%. This work was published in the year 2021. And this is a small molecule, long chain polymers. Then this is a research and development. In the university, researchers they developed this solar cells, but in commercial way, not commercialized in company, a Japanese company, Toyobo. So they synthesized a new material by a group of people, organic chemist people, using those new material to fabricate a solar cell. And they achieved a power conversion efficiency of 25%. It's the highest one in the literature. So they achieved the power conversion efficiency of 25%. So and also we this material, but they are not. They are not released that what type of material they have used for the fabrication of the solar cells, but they are saying this material can dissolve easily even in halogen-free solvents, so that by using those material they achieve this power conversion 25% power conversion efficiency. This research group optimized the solvents and the techniques of coating these organic solar cells on glass substrate also. They have prepared it on flexible plastic substrates. These are all some of the organic donor material used for the organic solar cell fabrications. So phthalocyanine and different polymers. Then these are all some of the organic acceptors. Generally available in literature. This is used for the fabrication of organic solar cells. This is some homoluminal level of organic semiconducting material. Organic donor and acceptor material. So that donor, how it is matching with the work function of ITU, and then PSSP dot is a kind of organic material. So you see that work function of low molar, how the low molar is matched with that electrode, like aluminum, gold, and calcium. How that low molar is matched with ITU. So their ultimate aim is that based on the homo-lumo level, they used to say that electron acceptor than electron donor, and based on the electrode also, we can say that electron acceptor material can act as electron acceptor and electron donor. It depends on the homo-lumo level, matching with the work function of electrode, work function of the electron. So the same material, you may ask a simple question, the same material, definitely sometime it can then either it can act as an electron donor, and sometimes it can act as an electron acceptor with respect to the of HOMO, LUMO, energy level matching with the work function of the metals. This is some work I have done that by using a small molecule based organic solar cell using evaporation technique. So 660 is an acceptor, and then carbon thioxide 660 is a heterojunction layer prepared it, plain heterojunction layer solar cells. And donor is a copper thioxide. I prepared all the floor layers by thermal evaporation technique. Achieved the power conversion efficiency about 3.8 percentage. So during my stay in Korea and Japan. So these are some instruments used for the deposition of organic light emitting diodes and organic solar cells, so that organic layer, I mean some blocking layer used to enhance the power conversion efficiency. So with that I stopped that organic solar cell part, maybe that I will give some idea about organic light emitting diodes. Other part is organic light emitting diodes. Definitely everyone is know what is organic light emitting diodes. Here we are using an organic material, so that it shows a promise of replacing liquid crystal displays and other lighting applications. Due to the low cost, ease of fabrications, brightness, speed, and wide viewing angle, low power consumption, and contrast. So OLED advantages over LED and LCD. So OLEDs are thinner and lighter, more flexible. So we are having wider viewing angles, so that high resolutions, so that pixel of less than 5 micrometer size is used here, and fast switching time. So 1 to 10 microseconds. The low voltage is required for the operation of OLED, so low power is being needed. So we don't require backlight and light generation here, thin displays. So small molecule, again that organic small molecule based light emitting diodes, first invented by this Professor C.W. Tank. Using ALQ3 is an organic emissive material. So first work was reported in the year 1987 by Kodak Company. So polymer-based light emitting diodes prepared by the Professor R.H. Friend Group and published a paper in the year 1990. So R.H. Friend Group from Cambridge Laboratory, Cambridge University. And this is a general structure of organic light emitting diode. So this is either glass or a PET substrate. So anode is that. So anode is the ITO. So and then hole transport layer, electron transport layer, emissive layer. The reverse concept. Then exciton is generated in the case of organic solar cell. Excitons are generated and dissociated. Then charge carriers are collected in the circle. But here, so that ultimate aim is to that recombine that the charge, I mean, positive holes and electrons at the emissive layer. When excitons are formed, then once exciton formed, it means so that emissions takes place. So from using cathode, so electrons are injected, and using anode, holes are injected, and then holes and electrons are recombined together at the emissive layer, and then illumination is takes place, emission is takes place. So that this is a different structure of organic light emitting diode. So that this is a energy level diagram of organic light emitting diodes. There's a cathode and anode. So different layer, emissive layer is sandwiched between anode and cathode. So from the cathode, electrons are injected, and from the anode, holes are injected. So once it is reaching that emissive layer, excitons are generated. So emission is takes place, light output is takes place. So this is small molecule based multi-layer organic light emitting diode structure. This is a polymer. Polymer means so blend. So we can prepare the polymer layer by simple solution technique. So we sand this polymer layer is prepared in between anode and cathode for a polymer based OLEDs, organic light emitting diodes. So this is the types of OLED. Generally, different types are there: passive matrix OLED, active matrix OLED, transparent OLED, top emitting OLED, and foldable OLED, white light OLED. So white light OLED is generally prepared by combination of red and green and blue layer, so forming in white. So that passive matrix OLED, then you see here anode and cathode. So anode, this one is anode, then cathode. Strips of anode and strips of cathode. The anode and cathode strips are perpendicular to each other, so that in between anode and cathode, organic layer, emissive layers are prepared, so that so where is the light emission is takes place means that at the light is emitted at the intersection of that anode and cathode. So anode and cathode intersection points are act as the pixel points. So that this is a passive matrix OLED. Then external circuitry is required to turn on and turn off the organic light emitting diode. So that this is space. So this type of structure is useful for the small screen applications. This type of OLED structure, but for active matrix OLED, full layers of anode and full layers of cathode. Be prepared between in between that organic emissive material. So here, thin film transistor matrix on the top of anode is useful for to turn on the pixels, which pixel need to turn on and turn off. So that that's the reason this type of structure is useful for large displays applications, and then less power is consumed in this type of PM. Less power consumed than that of PM OLED. So AM OLED is useful for large area display applications. It's a foldable OLED. That same organic light emitting displays are prepared on the flexible substrate. So nowadays you may see the transparent and flexible displays by Samsung mobiles. And the top emitting means that one side is completely that light is emitted at the one portion only through the cathode, and the cathode is prepared by transparent cathode. Once you prepare a semi-transparent cathode, means the light emitted at the top side. Another is a transparent OLED. Both the electrodes are transparent, means light can emit in both directions. Used to call it as a bidirectional light emissions. So this is the operation mode. So we are sandwiching. Organic materials are sandwiched between ITU and aluminum electrode. So the process of this is operation mode of OLED. What happened? We are injecting electrons from aluminum, and then we are injecting holes from ITO. So you see that this is the energy level. So injecting electrons, this is a low mode level of the organic emissive layer. So electrons are after injecting electron, transport of the electron takes place, and then at the center that exciton formation takes place. So transport of electrons from aluminum, and then transport of holes through the ITU, so that this side is electron, this side is and holes, then they recombine. Here that excitons are generated, here light emission takes place. So that this is a 4 important operations of organic light emitting diodes. So for this single layer concept, what happens? So if one electrons are there, passing, injected, and then reaching this place. So for the time, so 2 holes are reached in this area means, so it is charge carrier balance is difficult here. So that is the reason people are going for the 2-layer, bi-layer concept, multi-layer concept. So they are trying to increase the exciton formation in an effective way at the center. So they are trying to avoid the charge carrier imbalance. So once you use the multi-layer concept, they can balance the charge carrier reaching at the center. So once the charge carriers are balanced and reached at the center in effective way, then we will get a very good emission. And the emission, emission efficiency is very high. So there's a multi-layer concept they have introduced. This is a work function matching, metal work function matching with organic energy levels. So you see here anode and cathode. I told you that cathode and then anode. So how it is ITU work function matched with the HOMO. So same way that metal work function is matched with the LOMO level. So once it is exactly matched with the energy level, HOMO, LOMO levels, that then efficient charge injection is takes place, so that then we will get the maximum power conversion, maximum emission is takes place at the center of the organic semiconductor material, organic emitting material. So electron injection is by two-way metal into the organic semiconductor, and then one is a thermionic emissions, another is a tunneling process. So I don't want to go that in detail, so because it is again, so I have only this time, so that again that carrier balance is very important. So um, so this type of this is a emissive layer, so that you see here this type of or the structure. So what happens? So charge carriers are very difficult to reach at the center. So that what happened? They are introducing a multi-layer concept of different energy levels. So the energy level, we see that energy levels are gradually increasing. So that if you now injected a charge carrier, it can easily reach the that emissive layer. So that is the reason. So they are using a multi-layer concept here. So uh, instead of like this kind of a structure, then here it is very difficult to reach the electron to the emissive layer, because so yeah, that electron need to tunnel here, but this process is simply transport. So that energy level multi-layer concepts are introduced for the carrier balance, and then if it is carrier balance or effective means the one can achieve that very good emission at the emissive layer part. So these are some of the important things, and then I will random structure for getting a maximum efficiency. So that I would like to show some of the applications of organic light emitting diodes, like it is highly useful nowadays in cell phone displays. So almost all 90 to 95% of the displays are organic light emitting diodes displays. And then televisions, OLED TVs are very famous. Then that's the reason. Then you may get a TV of any size in future. So that OLED lamp for lighting applications, for OLED lamp, white OLEDs, so transparent window lighting. So all the materials, organic light emitting, all organic light emitting diode, all the materials in OLED, transparent material means then they can that OLEDs are looks like a transparent window. Once you turn on that light means it can start to emit. So that this is a pluses compared to that of inorganic based LEDs, but LEDs, organic based LEDs, we can tune, we can adjust the color also. So this 3D displays are possible. So in future maybe get e-papers already introduced LG displays, LG groups e-papers like our newspaper. So that is a display, so that no need to change the paper. That every minutes and every hour that news automatically and that change it in the paper e-paper. It is a flexible e-paper. So flexible displays. So it is available. If possible, my organic light emitting diodes. So organic mobiles, flexible mobiles then what is flexible mobile displays are introduced by Samsung groups. So lighting sources definitely white OLED playing a very important role in future. It may change the entire white lighting applications, traditional lighting applications in future. So and also white, that white your light is your display is white OLED displays, and they can insert into that car glass. So once you turn on it, then automatically that have your car navigation system. So once you once you turn off it, then automatically simply it is an windshield. So that this is some simple work that I have carried out in during my stay. That the ultimate using different this is structure, and this is an ITO, this is aluminum. So light emitting layer is ALQ3, and then cold transport layer is alpha UPP, and then this is electron injection layer. So work is that using inserting this electron injection layer, how efficiently charge carriers are injected into light emitting layer. So by using this electron injection layer, that is our results. So you see here, without using electron injection layer, turn on voltage is a 10.2. 10.2 means that this voltage is required to turn on your organic light emitting diodes. But with using electron injection layer for two different layers, you see that turn on voltage is decreased to 5 volt and 5.6 volt. So this is the work. So how efficiently electron injection layer injecting electron from aluminum electrode to that of our ALQ3 by using this electron injection layer. This is a very good work during my stay at Seoul. So that we have carried out so organic light emitting diode fabrication using organic small molecules. All are organic small molecules prepared under high vacuum condition using a thermal evaporation technique. This is a 3 mm into 3 mm pixel green OLEDs. So by using this electron injection layer, we have achieved that very good luminescence property. So almost so more than 5 times enhancement in the luminescence properties, and also we have reduced the turn on voltage from 10 to 5 volt. So during that time is a good work. That so almost 12 years before I was carried out this work. So this is a small work, small organic small molecule based one, and then this is summary of that work. With that, I will stop here. Maybe that if you have any questions and queries, please. Also, I would like to thank that organizer for giving me this opportunity to interact with the students. So I thank you all. Thank you.
Thank you, sir. Now, if anyone has any questions or doubts, you may ask now. Anyone?
Good morning, sir.
Yeah. Good morning.
So, what are the disadvantages of organic electronic material?
Sorry, madam. Please tell me again. What are all the?
What are the disadvantages of organic electronic materials?
Okay. Disadvantage means we may use the organic materials for low power applications. We cannot go for high power applications because the mobility of organic semiconducting materials are very low compared to that of a traditional inorganic semiconductors. So this is a very big disadvantage because once it has a very good mobility properties, and then we can use it for high power applications. But we cannot say it is a big disadvantage. That's the reason we are using it for a low power application, low power electronic applications like OLEDs and solar cells. These are all some. We cannot say it is a disadvantage. Organic solar cell always there's advantages compared to that of traditional inorganic based semiconductors.
Thank you, sir.
Anyone else?
Good morning, sir.
Yeah, good morning. Please.
Can you please tell me, sir, what are the materials that are best for solar cells?
You are asking the what are the material best for solar cell? Organic material. Yeah?
Yes, sir.
Organic
Yes,
material.
sir.
Yeah, organic material. Then it is. That's why I shown it PPT that Toyobo is a company in Japan. They have synthesized. They work years and years. It's almost they spend more than 5 years so to synthesize the optimal organic material organic polymers. So for a high power conversion efficiency, solar cells, for that they achieved 25 percentage. So it is very difficult to point out a particular material because there are large number of organic polymers and materials are there. So for recently, they are always. I mean, every year they are inventing, they are synthesizing a new type of organic material. So we cannot say like a traditional one, like a silicon. Uh, is a Till now that we are using a silicon for organic silicon for solar cell applications. We cannot say for like that in organic. So if anyone can synthesize a new material that is optimum for solar cell applications, and then that material may be a new one today. It may change it tomorrow by some other people.
Thank you, sir.
Any questions?
So,
Yeah, please.
so why the first OLED TV aren't planned like another, sir?
Sorry, you're not. I'm not understanding your question. Please repeat. Why?
Sir, first OLED TV introduce பண்ணாங்கல்ல sir.
Yes, yes, yes.
அந்த OLED TVs வந்து ஏன் சார் ஃப்ளாட்டா இல்லாம கர்வ்டா இருந்தது?
I don't think so that all OLEDs are flat only, not a curved. I never say that it is not OLED. It's a flat only. All OLEDs are flat only. So that's why I pointed out one it's a very important property is OLED is not having a wide viewer angle. I mean viewing angle problem. Suppose LCD you are having a viewing angle problem. Viewing angle means and then from the side particular angle then you cannot get a clear image on the LCDs. But OLED is not like that. So there is no viewing angle problem on OLEDs. So it's not curved. It is flat only from the beginning itself.
Okay, sir. Thank you.
You can also write it in the comment section if anyone has any doubts. Thank you, sir. Thank you so much for your time and words. We learned a lot from your presentation. I asked Ms. Masiha, 3rd BSc Physics, to thank our resource person.
Happy morning, everyone. To succeed, you need to determine something to hold on, something to motivate you, something to inspire you. I feel honored and privileged to get an opportunity to thank our honorable resource person, Dr. K. Sethuraman, Associate Professor, Central University of Tamil Nadu, Tiruvarur. We are greatly encouraged by your gracious presence and immensely benefited by your valuable talk on organic solar cells and organic light emitting diodes. I hope it will be a good platform to share knowledge about the methods of preparation of organic solar cells and help us to make our life brighter. Thank you, sir.
Oh, thank you, one and all. Thank you very much.
I now invite over Ms. S. Priya, 2nd MSc Physics, to introduce our resource person.
Every new beginnings come from some other beginnings end. It's my privilege to address you all on behalf of management and honored to welcome our resource person, the man with excellence, Dr. S.K. Das of GEM University, Odisha. He has a great understanding of the program and a great appreciation of what it takes to truly make one day national level webinar on emerging trends in the fields of material science on a path of progress. He was, ap- he was appointed as lecturer at National Institute of Science and Technology, India in 1999. He received, he received his PhD at Indian Institute of Technology, Kharagpur in 2000.
Yes, Masiha, can you please mute your mic? Please.
Okay, sister. Sorry for the interruption, sir. He was appointed as lecturer at National Institute of Science and Technology, India in 1999. He received his PhD at Indian Institute of Technology, Kharagpur in 2007. Later, he was appointed postdoc scientist at Max Born Institute, Berlin, Germany in 2007. After doctoral in 2013, he was appointed associate professor at KIIT Delhi University, India. At present, he is working as professor and at School of Physics at Gangadhar Mehar University, Odisha, India. He has received several awards. Best Poster Award at Second International Conference on Condensed Matter and Applied Physics, Rajasthan, 2017. A category faculty at KIT University, 2017. Postdoctoral fellowship from Rajaramana Center for Advanced Technology, Government of India, March 2007 to June 2007. Postdoctoral fellowship from Max Born Institute for Nonlinear Optics and Short Pulse Spectroscopy, Berlin, Germany, August 2007 to August 2013. Institute Fellowship for pursuing PhD at Indian Institute of Technology, Kharagpur, July 2003 to Jan 2007. And Institute Fellowship for pursuing Master of Technology Program at Indian Institute of Technology, Delhi, July 1996 to December 1997. He had a membership at Life Member Indian Laser Association and Life Member Indian Science Congress. He had collaborated with Max Born University, Berlin, Germany, Dublin City University, Ireland, University of Barcelona, Spain, Nanoscap, USA, and Astar, Singapore. He has published 92 research papers and he walked all over India. Never wait for a perfect moment. Just take a moment and make it perfect. I extend a glorious welcome to the enthusiastic and energetic research person. Welcome you, sir. I hand over to you, sir.
Okay, thank you, madam. Am I audible to you?
Yes, sir. Yes.
Okay. So, first of all, I'd like to thank the organizer and also thanks to all the participants to be here to listen my talk. So, I'm directly going to share my slides and go ahead with. And you can give your comments, suggestions, questions anytime in the text box so that I can address it immediately. Okay, and we may make it very lively or very interactive this session. Okay, so to go ahead, let me share the screen. So this you can just share the link. So is it visible?
No, sir, is it not visible, sir?
Not visible so far. It seems the net is so a little bit slow here. Just something is wrong here. Just a minute, I am fixing it. Stop sharing from sir. I will stop sharing. ठीक है सर since share ये स्क्रीन सर ये हाँ मैं आपसे डन गूगल मीट को ठीक है ना हाँ इंटरनेट एक्सप्लोरर को सब गूगल कम Okay. Now the screen is visible to you. So let
Yes, sir, it is visible, sir.
Okay. Okay. So the talk is on laser-induced functional materials. The outline of the talk is given here. Basically, I'll be giving the little idea on a particular types of materials or nanostructures that can be generated by using the lasers. Those are called as laser-induced nanostructures. And I'll give the correct applications of those type of structures and work done in this field by me. And also I'll give a brief introduction to the prospect and challenges of this field. To go ahead with this, so let us see what do you mean by laser-induced periodic structure first. Now all of you know the lasers. Lasers are very highly directed beam which can give us very high intensity. So and they can be easily focused to any material to a very small spot. Now I have in the picture here you can see here I have shown that a laser beam is focused to a sample here. This is a sample. And as soon as you are focusing a laser beam and you are controlling the fluence means the laser pulse energy per unit area. If you are controlling it well, then you can easily get the periodic structures like this. Okay. Now this is just a schematic diagram that I have shown here. Now this same thing is here in the real image here. This is the periodic structure that has been done on the zinc oxide substrate. Okay. Now the basic setup for this type of generation of this type of nanostructures or periodic structures is given here in the below as a experimental setup. Generally, I have written a femtosecond laser is used, but people can use some other lasers also like nanosecond laser, picosecond lasers. These are the lasers which give us the pulse output, whose time duration can be of the order of 10 to the power minus 15 second. This can be the time duration of the pulse. So if that is the case, then we call it femtosecond laser. And sometimes the pulse duration can be of the order of 10 to the minus 12 second also. These are called picosecond laser. And these are mostly used lasers. Sometimes nanosecond lasers are also used. Nanosecond means all of you know probably 10 to the minus 9 second. So these are also called as ultra fast or ultra fast lasers. Okay, which are mostly used in industry or basic R&D centers. These are high-end sophisticated lasers. And generally, this part you can see, this is the part which consists of a neutral density filter, lambda by 2 plate, polarizer. These optical components are used to control the fluence. Now we have taken a BS1. BS1 stands for the beam splitter, where we used to take a part of the beam and we used to measure the energy here or see the pulse. Sorry, we used to measure the pulse energy here, and we used to see the laser beam profile here. Okay. Now and through this lens we have focused it to the sample which is generally placed in a XY stage, and the XY stage has to control by a computer. Okay. Now and this during this processing you can image the things or sample by long distance microscope. This is the basic setup for doing the experiment which we have in my laboratory. at KIT University, and here also I recently joined. Recently, already 1 year is there. So we have also set this type of system here, but we are not using the femtosecond lasers, but we are using some low cost laser because femtosecond lasers are very expensive. Generally, not everywhere you can find them. Okay. Now coming to the next, there are a couple of examples I have shown here. You see, this is the periodic structure that has been gone on titanium dioxide, and this is on silicon. Now, what I mean to say that it is the process which you can easily apply to any kind of solid state materials. Maybe it is a semiconductor, maybe an insulator, or maybe a metal or polymer. You take any materials by the same procedure, you can generate the nanostructures, which are having highly periodic, well defined. You can see this image here, very well defined periodic structures. Now you can see this is the scale here, 300 nanometer. Now you can see the periodic size can be down to, now for example, you look at these groups here. These groups are less than 100 nanometers. Okay, and the period is also less than 100 nanometers. So for doing such small structures, periodic structures, you have to go for very advanced lithography technology like X-ray lithography or E-beam lithography, etc. E-beam or X-ray or FIB, focused ion beam type of lithography we have to go. Okay, and all of these techniques are very expensive, and they do have some disadvantage which we can easily overcome by using this technology. What I am showing here. Okay, and some other basic characteristic of such structures are like this. Generally, it has been observed the periodic structures that are generated can have the period of close to wavelength. So such type of periodic structures are called wavelength structures or low frequency structures or low frequency laser induced periodic structures, which is very popularly known as in laser science and technology, LIPS or laser material processing group. It is very popularly known as LSFL, low special frequency LIPS. Then there is another kind of periodic structure that is being generally observed, whose period is much more than the wavelength. So those are called as short wavelength structures, which are short form SWL. And if your period is very small, obviously frequency is very high. So in that case, it is called as high special frequency laser induced periodic structures, HSFL. So these are these two types of leaves are found, and the orientation of the structures are also very well defined. It has been found. It can be either perpendicular or parallel to the polarization of the laser beam that you are using. Generally, laser beam can have the polarization that we can easily define. Probably you know the polarization. It is the direction of electric field of the light beam that define this polarization, and you can easily control this polarization. And this polarization will decide the period direction. Okay. Now, some other general observations are like using ultra fast laser, the laser that I told you, either femtosecond laser or picosecond laser. Those are ultra fast laser. In this type of laser at low fluence, generally low SWL means sub-wavelength lipid structures are found, whereas the other type of leaves, like which are wavelength leaves, are found with CW laser and nanosecond laser. And sometimes it is also observed with ultra-fast laser, but at high fluence. Now you see, you have a lot of control over your process. You can change the period size by changing the fluence or changing the wavelength. Okay, you see, if you are changing the wavelength here, then periodicity can be changed. So So these are the and you can also control the orientations. Now some other advantages are there. I'll show you in my next slides. Now some other observations are like this. Generally, in the laser beam, the fluency is not uniform all across the beam unless you are taking very special care. In such case, the laser beam intensity is highest at the center of the laser beam, and it gradually decreases to the edges. In such case, the periodicity gradually changes. You can see periodicity of these structures gradually decreases. Now, about this figure, I'll tell you. This work I did at Max Born Institute. We had given a theory to explain this phenomena, which is widely used by various scientists to explain this. It's a very peculiar phenomena. Why such structures are coming? Uh, it's puzzling the scientists since long back. I can say since its innovation. Okay, so I'll show you some of the models that can well explain this phenomena. Now, before going to that model, which may be a little bit boring for you, I like to go for application of such periodic structures. And let me tell you what this N stand for. When these structures size are around 100 nanometer, we call it laser-induced nanostructures or laser-induced periodic nanostructures. So some of the examples I'll show you here. You see, this is one applications where you can control the hydrophobicity of the surface of any material. For example, in this case, the silicon surface has been processed by the laser, and various structures are generated. For example, in this case, you can see here, this was done at a fluence level of 2.2 kilojoule per meter square. These structures were periodic. When the fluence was increased from this level to this level, the structures were found to be changed, and you can see at some angle or at some fluence there can be conical structures. Such conical structures are very useful for various applications. One of the applications is being shown here. You see, this is a water droplet. Water droplet. This one is a water droplet. This is a microscopic image of a water droplet on silicon surface, which is plane. Now you see, when it is plane, the water droplet is it is sticking to the surface. Okay. Whereas when you do the microstructuring here, in this case, then water droplet is forming a spherical shape. What does it mean? It means that as soon as the water droplet hit on it, it can easily roll away, and no water will be stick into the surface. So you just imagine you have a microprocessor, or you have some other electronics devices that contain silicon microprocessors, and when it is getting dipped into the water, it is not getting affected. It is because the water cannot wet it. That means as soon as water is falling on it, it is easily rolled away. So you are creating a hydrophobic surface. So it's a very interesting topic for industrial purpose. And nowadays, people are using for various applications. Like you see in aeroplane, you can create such structures and make the surface hydrophobic, so that no water droplets in the high altitude, no water droplet can stick into the surface of the aeroplane body. Okay, that will be a good advantage. Okay, so so a lot of research is going on in this direction in the industry level, and some of the companies are also using this type of concept. Okay, I'll tell you about those things in my next slides. Now you see, we can trap the light. I told you about these conical structures, how it can be formed. These conical structures, you see, these conical structures, they show very low reflection. you see the reflectance behavior of this surface, you see it is close to 0%. Okay, it is done by a group in USA in 2011, and here the beauty is that all the light that fall on it will be getting absorbed. So in such case, the silicon will be called as black silicon because light is getting absorbed. And you can ask me why it is getting absorbed. It is getting absorbed because of the multiple reflection here. You see, when you have a conical structures like this, the light can fall here, get reflect like this, and you can see they get trapped here. Okay, every time in a reflection it will be absorbed on the surface, and after multiple reflection whole light can get absorbed. So it can give us very highly absorbing material, therefore it is called as black silicon. Okay, so and you see when yes, silicon surface is absorbing much light, then its efficiency has to be very high. So in all the optoelectronic devices, it will be useful. One example is being given here. You can see in the black car, this is the quantum efficiency shown by black silicon, whereas it is by the polysilicon. And you can see in the black silicon, it is showing much better behavior. Some other properties are like this. You see in the cathodoluminescence, generally when you apply the electric field, then light can generate. Now it has been observed, if you process a portion of the metal surface or filament, like here in this case on, if you process a particular region by using laser and create such nanostructure, the emission capability of that region will be much higher. So it has been shown by a group by a Stanford group, whereas the previous okay, generally Stanford and Harvard and other premier institutes have done such experiments. And in India, very less people have done. I started this work around 6 years back, and I'm getting good results now. I'll show you those results later on. Now you see, friction of a surface is depend on the roughness. And you see, because you are creating the nanostructures or any structures, you are controlling the friction. So you can control the friction, and sometimes you need the friction for some applications. So you have a control over it. Now, some other applications are like plasmonic applications. Generally, if you have some metal nanostructures, that means nanostructures over the metals, then they can create one quasi particles, or you can see the one phenomena called surface plasmon polaritron. Okay, surface plasmon phenomena generation can be there. So and this surface plasmon behavior can give us various color appearance to the metal surface. You see, in different as soon as you are making the aluminum surface, creating laser-induced periodic surface structures. This LIPSS stand for laser-induced periodic surface structures. Aluminum stand for obviously aluminum. Then you can see the color of the aluminum change from this to this. That means it's a gold appearance you are getting. So you can imagine you are creating gold out of aluminum. Now you can imagine the advantage of such things. People are much fond of obviously gold, and obviously if they can get gold ornaments in much less cost, that will be nice. So a lot of work is going on this direction also. Now some of the works that I have done here is shown here. First of all, I like to show here this work. This work was done using a cylindrical lens. Okay, lens can be either spherical lens or cylindrical lens. Now, in this work, we have shown that if you take a cylindrical lens here that I shown you, cylindrical lens, and you focus it here onto a material, and generally the dimension of the cylindrical lens can be of the order of 1 centimeter. Okay, whereas you can see the structure of the periods that can be of the order of 100 nanometer. Now, if I answer is just see 1 centimeter divided by 100 nanometer, it will be 1 lakh, not lakhs. It will be 1 lakh. That means in a single scan you can get 1 lakh of nanostructure at a time. Whereas in a focused ion beam, you generate 1 nanostructure at a time in a single scanning. That means this process is 1 lakh times faster than the focused ion beam type of arrangement. Okay. So now, for detail, you can see this publication of mine. Then this is a recent work, laser processed micro groups based black silicon. Now, as you see, silicon photovoltaic cell has a huge market. At this point of time, almost all silicon solar cell, almost all solar cells that you are looking in the rooftop, maximum of them are, or majority percent of them are based on silicon solar cell, because it is a well-established technology. Okay, you can see it has a very huge market. Okay, now. That you know, so I am not going in detail. So my work is in this direction. And you can see some statistic I have given how it's a very growing field. So I'm not giving in detail. Now you see, at present, the mostly the solar spectrum here. This is a visible spectrum that is getting observed by the silicon solar cell, the conventional solar cell. But as soon as you make the black silicon, then it has been observed that because it is based on trapping of light, and also sometimes you can go for doping of the silicon so that you can tailor the band gap, and you can go for lower band gap also, and you can observe this spectrum also. Okay, these are in NIR, and NIR stand for infrared, near infrared. Okay, or IR called infrared. So this type of region can be also utilized. Okay, and as I told you, it has a big market here. And this I am not going in detail because you know, and from the previous speaker probably, or maybe it's a standard. Okay, but quickly I'll show you. At this point of time in industry, they are using this standard technology, chemical texturing, to create the black silicon or textured silicon before making the solar cell. Okay, solar cell is nothing but a PN junction. Okay, and to reduce the reflection, they have to do the texturing first. And nowadays they are doing the chemical texturing. The biggest disadvantage of this texturing that you cannot use the chemicals again and again. Once you use it, you have to throw it. Okay, so it is expensive work, and sometimes it is also hazardous to the environment because you are throwing that some chemicals to the environment. Now people have also gone for template-based nanowire generation, and we are by going for some CBD type of process. You can go for, or reactive ion etching. You can go for creating such some nanostructures to reduce the reflectance. Now this is the black silicon created by laser that I told you. This I did in the KIT University. Okay. Now this I told you. Okay, some other applications are like surface enhanced Raman spectroscopy. Probably many of you know that this surface plasmon that is generated on the any surface in presence of the metal and light, so metal nanostructures, it can enhance the electric field to a high value. So in such case, you can enhance the Raman spectroscopy output to a very large value, and you can detect even the single molecules. I have done some experiments on this with collaboration with my colleagues. So that I'll show you quickly. Okay. Now, as I told you, I'll tell you about the detail about the work that I have done in this. Basically, we have done to start this work in India. It was a difficult task for me because in kit, they are never in the beginning stage. They have not provided us so much facility. At that time, kit was not so famous. Kit is very famous at this point of time. It is just similar brand now. As it's a private university, it is a similar brand like VIT, Hello Institute of Technology, or Beach Pilani. Okay, so when I landed up there, I first started doing something that can be done with a very low cost. Just see, I developed a thing called laser workstation attachment, LWA. Let me tell you what is a LWA. LWA is a laser workstation. General laser workstations are available by the from the company, which are mostly American developed countries. They used to sell this type of workstation. In India, generally nobody used to develop such workstation. So what I did actually, I had got one small project from CRB. So there I proposed that I will develop a attachment system which will consist of the beam steering elements like some mirrors and focusing things. And here you see I have not integrated, but I have kept an option to interface the laser beam here. Okay, so what is then the beauty of this? The beauty is that such type of system can be easily created by two lakhs also. Okay, now this type of system can be interfaced to any ledger. So now this ledger, we didn't have the ledger at that time. I was going to various places like Niger. I was getting this system to Niger or IIT, Kharagpur, okay, and some other places, and I was interfacing to their ledgers, and I was doing my job. Okay, so now you see, previously this was not possible because if you want to buy a ledger workstation attachment, ledger workstation, then you have to spend around at least 20 lakhs because the most expensive part is ledger. If you are using nanosecond ledger, okay, and it's more than this. Now you can see I have without going for this, I have done the work also. And if you are using the femtosecond ledger, it can be of the value of 1 crore, sorry, 2 crore or more than that. Okay, so now you can understand I was availing the facility because in IIT Kharagpur they do not have any expertise on laser material processing, but they have the femtosecond ledger, and femtosecond ledger they are using for various other applications. Okay, because it's a very useful device and can be used for many applications. So they were focusing on different other applications. I simply took my device there and I interfaced to their ledger. I did experiments. So concept was very much appreciated by government of India. Called one organization is there, probably you know, NRDC. It's a government of India organization. So it generally go to different university and they try to find the discovery that can they or invention that they can give the financial support to do the patent filing. So they have given us the financial support to file a patent on this area. And this laser workstation we are generally using for all the experiments that I have shown here. So this is the real image of the things. This is a laser that I have used. I have used a very low cost laser called nitrogen laser. This is a gas laser uh, uh, of 4 nanosecond pulse duration and around 170 microjoule pulse energy. Okay, and this through these two beams, the pinholes, I have interfaced it to the this LWA. This is the LWA. This is the outer view of the LWA, and this LWA can be controlled by a software program that we have developed in LabVIEW. Okay, so this was developed by us in LabVIEW. So we have expertise on this. This is the outline of the front end of the LabVIEW program. So probably most of the participants cannot understand. But for your information, let me tell you, we can do these things for you or for ourselves. For anybody who wants, we can do that thing for you. Okay, this is the interior view, inside view of the setup that we have used. That I was telling that it was being approved and already filed the patent. Now we have done the characterization. We have done IUC. These are very uniform theory structure we have done. This is optical microscope image. Then we have gone for a PSCM to see the morphology that has been created. We have done the programming to the stage such a manner that after going to a certain step, it will stop for some time. Then it will go ahead. So in such a manner, it will create a groups here. So these are called as V group shape. Okay. So this V group shape can trap the light here. You can. So you see, we have reduced the reflectance to a very significant level, less than 10% from around 45%. Okay. So this is of its first kind in India, which has been done. Okay, so we have given this explanation. And detail of these publications you can find in my Google Scholar uh, web pages. Okay, I'll show you some of this. Now, second application, so that now, okay, let me tell you about these things. Now we are also doing the experiment to do the real solar cell development. Okay, now this second application I can say you that we are doing or we have successfully done, that is photocatalysis activity. In this activity, it's actually catalysis. You know that it enhances the chemical reaction. One of the chemical reaction you can see in the example here, splitting of water into its constituent to hydrogen or and oxygen. So before going ahead, I like to ask the participant one question. Then I will go ahead because I want to know whether my participants or audience are listening anything or not. Okay, dear participants, are you listening? And is the topic understandable to you, or is there any difficulty you are finding? Please give your answer in the text box. In the text box. Yes. Okay. Fine. Okay. Fine. Okay. Good. Thanks. At least one, two response I would like to know, and so I will go ahead with. So let us see what is the photocatalysis activity. Now you see splitting of water, let's say to hydrogen and oxygen. Now you see this is a very such type of process is very difficult to do. It's a chemical reaction, very difficult to do. Now you see Prime Minister is saying that we can run our vehicle by using the water. What is the basic mechanism? The mechanism is given here. You have to split the hydrogen, so water into hydrogen and oxygen. Then you can use this hydrogen as a fuel. Okay. So this is the philosophy. So this is the green fuel generation. And you see, in Earth we have plenty of water, and the available water can go to billions of years, and for supplying the energy to the mankind. So it's not also dangerous. So people are trying their best to go for such things, and these things can be only by possible by presence of nanostructures, semiconductor nanostructures like titanium dioxide, zinc oxide, or similar semiconductor materials in presence of visible or UV radiation. And here actually for titanium dioxide, the band gap of this material is around 3.3 electron volt. So generally the basic mechanism of such things is not, I have not given here. The basic mechanism of such process is that as soon as a photon is coming, then electron will generate, so jump from the lower level to higher energy level. and this free electron will now do the necessary chemical reaction. It will chemical reaction for splitting the hydrogen. This is the sorry, splitting the water. Similarly, you see here, I have shown that you see very often you can go for dye decomposition. Dyes are the very dangerous byproduct or waste product of textile industry, paper industry, pharmaceutical industry. So they release this dye to the underground water or surface water, which are dangerous very often. So now before doing this, one must have to go for decomposing this dye. And the dyes are generally bigger molecules, organic molecules, and you can decompose harmful dye decomposition using this presence of titanium dioxide. Now, there are several applications of such things like antimicrobial application. That means you can kill the pathogens like bacteria or viruses. You can kill by the same principle. You can go for self cleaning, anti-fogging, hydrogen production. That's just I told you about that, and the pollution control that I told you now. This where dye decomposition is the pollution control or waste water management. Okay, these are various applications now. And there are a couple of advantages of this. You can see here. This I'm not going to show in detail. And you see, it is also a very big market actually. It's a $1 billion market again. Okay, and I have given an analysis here, but you can see I would like to show these things. You can see it's a $4 billion market now. Okay, now we have created such a periodic, highly periodic structure on titanium dioxide structures. Then you see we have done some kind of analysis called 2D FFT. FFT stand for two-dimensional fast Fourier transformation to find the periodicity of such structures. We can easily find out that. Then we have shown that. So this is being created on silicon. Then we have deposited the metal surface on that. Then we have shown that when there is silicon leaves and we have blown the titanium dioxide by a high pressure sputtering process. HP sputtering stand for high pressure sputtering process. Then the dye decomposition takes place to a much. You see, this is a graph showing the concentration of the dye with respect to time. Okay, you can see the concentration of the dye was, let's say, 1 in the beginning before doing the photocatalysis. As soon as we are doing the photocatalysis, the dye decomposes, then this concentration reduces. Now you see here the concentration has been much lower in presence of the leaves, whereas in the non-leaves it was not going down. Okay, so it shows much higher efficient dye decomposition. These leaves. Similarly, with low pressure titanium dioxide, we have tested, and the results are here. And we have gone for some analysis. These are the standard analysis to find out the reaction rate constant, how fast the sample can decompose. Then we have find out the ratio. Generally, if you take this C by C0 and take the ln C0 by C and take the time versus ln C0 by C graph, then it will come some scarp, and you can do a curve fitting, and this is called pseudo first order fitting. You can go for second order fitting also, but mostly the reactions are first order. And I found that the enhancement of the reaction rate can be 2 times using leaves. Okay, similarly here in the low pressure also we can enhance it. Then the possible cause we have given here, we have done the AFM study. Okay, and we have found that the roughness has increased many times. So that has caused this photocatalysis enhancement because the photocatalysis efficiency is much higher with nanoparticles or maybe larger surface area. Okay, so we have given this cause, and we have done some other study that I am not going to say you. We have done the this another study also. You see, this has been already published. Now you see. We have created such periodic structures on silver substrate, and such substrate can be behaved like surface enhanced Raman spectroscopy detections. We have my collaborators in Germany have done actually DNA detection by this substrate. Okay, then. And there are a couple of things why such structures are there. A lot of theories are there: Jaipei theory, nonlinear Jaipei theory, freezing capillary theory, surface plasmon theory. So basically, in these two theory, we have given contribution, and it is working very fine actually. For example, I can show you quickly how these are working, or this how. For example, Jaipur theory was given long back in 19. It said that the periodic shift. It said that there is already rough surface. Any material has some rough surface, and as soon as the light is coming onto it, then it gets scattered, and the scattered radiation and the incoming radiation will interact, and they can superpose and gives the periodic structures. And they predicted that this structure size should be lambda or in the metal, and the dielectric should be lambda or lambda by 10. So lambda by n. N means the refractive index. But it has been found that the periodicity can be much lower than lambda by n. For example, I am using 800 nanometer radiation lambda, and the refractive index of the material is let's say 2. Then you can see periodicity of the lowest should be 800 divided by 2 should be 400. But experimentally you have seen that you can go up to 100 nanometer. Why so? So the or maybe 200 nanometers so. So then we have given that the second harmonic radiation is responsible for this. As soon as light is falling on such rough surface, then second harmonic generation can take place. Second harmonic generation is a phenomena by which when laser light beam fall onto materials, its frequency is doubled and wavelength is halved. So this is called second harmonic process. So when lambda becomes lambda by 2, then you can see the periodicity will be much smaller than lambda by n, and this is fitting much well. Okay, and also interestingly, we have given another theory that this refractive index is not constant. It is dependent on the fluence. So when it is depending on the fluence, so with the change of fluence, the n value will change and the refractive the periodicity will change. So this is exactly showing the experimental, justifying the experimental behavior. So, and another thing is another theory is this one is freezing theory, capillary freezing theory. It says that as soon as light is laser beam fall onto the surface, it creates a molten region, and this molten region have very high temperature, and the room temperature is around 100 degree, and the molten region can have the very high temperature around 1000 degree. Because of such large temperature gradient, it will immediately this wave will freeze, this molten liquid which is forming a wave that can easily or instantaneously freeze and can give a periodic structures. That was the theory given, but we proved it wrong. You see, we have shown that periodic structures can be generated. Just see, these are the periodic structures, but there is no signature of any melting here. So such signatures are maybe because of the interference, and here this period follows very well to our second order SAG based Jaipei theory. Okay. And here also I have shown that extremely soft wavelength can be done without any melting process. So, and another theory we have given, this surface plasmon theory, that that refractive index change can be explained by taking the actually, you see this Drude model. The Drude model said that the refractive index can change by the amount of the carrier generated. N stand for carrier generated by the presence of laser beam. So when this is changing the plasma frequency, this electron create a plasma will changes. The sorry, dielectric constant will be changes, and our because our refractive index depend on this value, so that will also change. So that we have done some theoretical simulation, and here I am not going in detail because it will take a lot of time. And interestingly, we have shown to some region where it was very well fitting, and we have shown it. This observation were there in the nature, and we have really predicted very well. But you see, the dotted lines are the experimental observations, and the blue line is the theoretical curve that we have given, the theory we have given. It is very highly cited paper now. I'll show you this thing in detail in the Google Scholar. Okay, now I'll go for the prospect and challenges. It's actually, you see, there are already large number of applications. Many more applications can be done. If you have any idea, you can contact me, and maybe we can collaborate. And there is plenty of reduction, scope for reduction of the cost. For example, people have done most of the experiment using femtosecond laser. But in India, I written SCRB for doing this experiment using the nanosecond laser, okay, whose cost is very less. And I really saw that whatever the femtosecond laser is giving, similar result I am getting here using the nanosecond laser. And further scope is also there for reducing, and understanding the mechanism, particularly surface plasmon polarization based mechanism that I have given here, this type of things. Some more pump of spectroscopy or other experiment can be done to understand or confirm this process. Okay, and before I end, I like to I have a couple of projects running. One of them is SCRB, and you can see the project title: Studies on Growth of Laser-Induced Hyper Black Silicon and the photo-excited carrier dynamics for cost-effective and efficient photovoltaic applications. And actually, I am extremely thankful to Professor Dr. P.K. Sao from Niger and Ritik Sir from Niger, who have extremely kind enough to help me in doing this experiment, in particularly characterize some things there. Also, I am thankful to my PhD scholar who have done the experiment mostly. And this is the first group of students. These are the students. Many of them already completed. 7 of them have completed, and 3 of them are now continuing, and few more students are there. New student image I have not given. They are continuing here. So I am also thankful to them. So this is the my group in Germany, where we did various work, and I also thanks to them. Okay, and also I thank all of you for your kind attention. Okay, now what I have done. Madam, any question from anybody or for detail? Hello, Madam, are you able to listen me?
Sir, yes, sir, we are listening, sir.
Okay, I have already done. now maybe a couple of questions I can answer. So what should we do, madam, now next? It seems there is no question. For detail of my publication, probably you can go to Google Scholar and type my name. You can see these are the various publications, and you see this the theory that I told you here. You can see it's very high, very highly cited here. You can see highly cited here. Similarly, this other papers are also very highly cited here. This is the extended area Titan cylindrical lens work that I told you, and multiphoton surface plasma collision behavior type of theory that has been given here. Okay, so you can refer these things for detail. Okay, and you can even contact me if you like. Okay, madam, then shall I log out?
Thank you, sir. Thank you for sharing your informative presentation. And if there is any question, you can ask now, students. Okay, thank you, sir. I ask Ms. Mafi. I now invite Ms. A. Lavanya, third BSc Physics, to thank our resource person.
A cheerful good afternoon to one and all present here. Gratitude creates the most wonderful feeling. It can resolve disputes, it can strengthen friendship, and it makes us better men and women. With esteemed happiness, I am here to conclude this section by showing my gratitude on behalf of the management and the Department of Physics. I take my opportunity to propose the vote of thanks. First and foremost, I thank the Almighty God who always governs us by His action. I extend my gratitude to our Honorable Chief Guest, Dr. S.K. Das, Hidden Professor, School of Physics, Gangadhar Mehar University, Sambalpur, Odisha, to take out time for his busy schedule to grace the event. Thank you, sir, for inspiring, encouraging, and motivating the students to dream about the scientific knowledge with your words on this special day. Once again, I thank you for your presence and contribute to make this webinar a great success. Thank you.
Thank you, madam, and thanks to all participants and the organizing committee members. Thank you all. Then I'm signing off.
Okay, sir. Thank you. Let us take a short break for lunch. Please be back at 12:55. You can use the same link to join the meeting after lunch break. Thank you.
Korea. Most prominently, CSIR and DST Senior Research Fellow is honored by the Indian government on 2003 and 2004. In all the exile, she has presented 28 international journals and also EXO conferences. All about to the session, it is now my pleasure to welcome on behalf of all the younger minds, the admiring woman whom you've been waiting for, Dr. S. Bhuma Devi, Department of Physics, Tiruchirappalli. Welcome you, ma'am.
Thank you, Sweta. Thank you for the nice introduction about me. So I am very happy to deliver my lecture in this occasion. Thank you so much, ma'am. Thank you, ma'am. I thank the organizers for giving me this nice opportunity to deliver my lecture here. Ma'am, please let me know whether the slides are being shared. Could you please hear me?
Yes, ma'am.
Ma'am, whether the slides are being shared, ma'am? Could you see the screen, ma'am?
No.
No,
Okay,
ma'am.
just wait a moment.
Okay.
Let me check. Please give the acceptance to my slides. Please give acceptance to my slides, ma'am. Sharing. Grant permission. Accepted. Okay. Ma'am, still it seeks permission. Could you please check it? Please check the permission. Ma'am, it's saying can't share the screen. Give permission to see my slides.
Ma'am, good afternoon, ma'am. Wait a few minutes, ma'am.
Okay, ma'am.
Dear participants, here is some technical problem, so please wait a few minutes.
Hello.
Ma'am, visible, ma'am. Your slide is
Slides are
visible.
visible, ma'am.
Yes, ma'am. Uh,
Okay.
that is you are presenting to everyone, so that one is
Okay. Okay.
visible. And now visible, ma'am.
Okay, ma'am. Okay, ma'am.
Okay, ma'am. Thank you.
Thank you, everyone. Good afternoon to all of you. So today I'm going to give a lecture on applications of organic and quasi-phase matching devices in nonlinear optics. So what is nonlinear optics? Let me give a brief introduction first. Before entering into nonlinear optics, we must know something about linear optics. So what is linear optics? You know well all, we have conventional light sources. So these conventional light sources have very weak light intensity. So nonlinear optics, in other words, we can put it as optics of weak light. So what is weak light? Basically, the electric field depends on the intraatomic field. That is, the electric field intensity is less than the intraatomic field. So what is intraatomic field? So if you consider, for example, interaction of light with a material medium, any medium, right? So the light is going to pass on a medium. So right side, you can see the energy levels. So here, this is the technical part and I am saying the theory behind it. So the electric field of the light interacts with the material medium. You have virtual energy levels. The red arrow shows the input energy. The photon energy. So it is going to catch one of the energy levels. Energy levels means, you know, all material medium is consisting of molecules and atoms. The atoms in turn consist of nucleus and electrons. So it is going to capture one of the energy levels and the input light is going to come back to the original ground state. So it is basically a reaction, a transition between ground state to the excited state. So here, in this case, the applied conventional light sources, whatever you have, LEDs or incandescent bulbs, normal bulbs. So this electric field intensity is very much less when compared with the atomic field intensity of the material medium. So here, when the light is passing on such a medium, the light is getting deflected or delayed. The path is getting changed after the light falls on the medium. It may be getting refracted or diffracted according to the conditions of the medium. So here the frequency of the input light remains unchanged. So here in this case, the refractive index N of the medium, it is independent of the light intensity falling on it. So this is what we call it as linear optics. The linear optics obeys the Snell's law, light laws, basically all laws of reflection and refraction. Whereas coming to nonlinear optics, we can call it or define it as optics of intense light. So what is intense light? So we all know the invention of laser followed in the year 1961 by T.H. Maiman. He invented ruby laser. Basically lasers, they are very strong light sources. That is, the electric field strength will be the order of megawatt per centimeter squared. So such a strong light intensity is required to disturb this intra-atomic energy levels. That means the electrons are being pulled towards by the action of electric field. So here, the electric field intensity is approximately equal to the order of intra-atomic field strength. So here, it modifies the electron distribution energy levels. You could see the right-hand side figure. The input and photon energy, it is just like first falls on the virtual state, then it is reaching to the higher upper excited state, and you are getting the back absorbed photon of energy h nu. The emitted photon will be higher in intensity or lower in intensity according to the nonlinear effects. So this laws will be violated. Basically, it doesn't depend on the linear optics. This particular process is called nonlinear optics. Why? Because it has a deviation from the linear optical basic ruled laws. In this case, the intensity, the refractive index N depends on I, the intensity of the light source. So basically, nonlinear optics gains popularity or gains importance with the advent of laser light sources. So what is optical nonlinearity? Again, this is a small slide for your basic understanding. Applied electric field distorts the electron cloud and displaces the electron. So you all know the atomic structure, atom structure. Atom structure consists of nucleus in the center, surrounded by the electron cloud. The blue figure, this dotted arrow shows the creation of dipole moment with the advent of laser light. So you can consider this situation analog with the mass stretched by a spring. right? So separation of charges, that is the electrons are being pulled towards the one end, whereas the nucleus will be shifted on the other end. So it gives the separation of charges, thus by rising to the dipole moment. And basically the cumulative dipole moment gives rise to the polarization. So this is the spring constant rule. The restoring force is given by minus kx. K is the restoring constant and x is the displacement of the electron shift. So here again, this is yet another figure. This is the basic light equation for linear and nonlinear optics. The induced cumulative polarization P of E is dependent on epsilon naught, that is the dielectric constant of the medium, and x chi1 E plus chi2 E dot E plus chi3 E dot E dot E. So the first term on the right hand side is called as the linear optics. So this obeys the basic laws of reflection and refraction. The second term is the chi2 is the nonlinear susceptibility. It depends on the square of the electric field. That means you have to apply the twice the field strength of the input intensity of the light. So this is equal to P1 plus P2 plus P3. P1 is the linear part and PNL is the nonlinear part. So in this figure, you can see the molecule or atom which is interacting with the input wave, and the emitted wave is same in the color in the case of linear optics. Whereas in nonlinear optics, you could obtain the new frequencies, which is represented by the blue arrows. So, what are the nonlinear effects you have in this particular talk? I am going to highlight only two basic effects in which I am being currently working with. One is second harmonic generation. Other one is difference frequency generation or optical rectification. So, all these properties are basically second order nonlinear effect. So what is the second harmonic generation? You could see there is a fundamental. What is fundamental means the input light intensity. For example, you are going to take a 1064 nanometer fundamental IR beam. You are going to pass it on a nonlinear medium. That is any crystal which contains the lacks inversion symmetry. I am coming to this point later. So you are going to launch a light with the frequency omega. You are going to generate 2 omega depending on the property of the material medium. So this is called a second harmonic. Omega is omega, input is omega, and output is 2 omega. So what happens here? Basically, H cross the photons combines and you are getting H cross 2 omega, the output in blue color. So below this, you could see the phases of the input waves. The input wave is represented by red wave and the output wave is represented by green wave. Basically, the phases means you can see, in other words, the crest and trough of the each wave should coincide in order to generate a coherent output. So if it is not matching as shown in the figure, what will happen? For example, if the crest of the red color wave meets with the trough of the green color, there will be a phase mismatch. The generated second harmonic will be very less intense and it has a probability to convert into fundamental or depends on the phase mismatch factor. You could you can obtain green color output, but the intensity will be very less. So how to solve this problem? So in order to compensate the phase mismatch, we have to achieve phase matched second harmonic generation. That means you can get full efficiency out of the input omega wave. You can convert almost 80 to 90% of the input wave into 2 omega. But practically, is it possible? Let us see. So example, what is the, you can take a birefringent material. You know all what do you mean by birefringents? So the refractive index of the any crystal varies with the direction. You take any crystal axis with the length, breadth and sufficient thickness. So along the x-axis, that is the length, the refractive index will be one value. Along the breadth, the refractive index will be another value. So in other words, you can say define it as anisotropic material. That means the refractive index varies with the direction. So you can have different refractive indexes along different axes of the crystal. So delta Kb is the phase mismatch factor. So it could be solved by this particular equation, which depends on the lambda, which is the wavelength of the input material. N2 omega is the refractive index along the second harmonic output, and N omega is the refractive index of the fundamental wave, right? So here, the nonlinear crystal, what are the limitations? It must be birefringent, that is, it should be anisotropic crystal. You cannot obtain this in isotropic material, such as glass. So it is basically a second order effect. And it is sensitive to the angle of incidence, how you mount the crystal. And the refractive index should vary along the polarization axis. Next one is the phase matching. So coming to this, phase matching, there are different ways to achieve a phase matched output. One is the angle tuning, the other one is temperature tuning, the other one is birefringence phase matching. There are three types of phase matching. I have told you about birefringence phase matching. So here you could see there are two graphs. One is NY, one is NO and other one is NG. NO is the ordinary fundamental output and NE is the extraordinary wave. Just you take a simple analog situation. All of you know about double refraction, right? In calcite crystals, when you pass a light along particular axis, along the optic axis, you could see ordinary ray and extraordinary ray emerging out of it. Similarly, when you pass a laser light through a nonlinear medium, you could see the fundamental ray coming along with the second harmonic ray. So this particular wavelength, it will have the twice the frequency of the input wavelength, or in other words, half the wavelength of the input wavelength. So this is what we call it as phase matching. In angle tuning, you have to rotate the crystal. Practically what we do in lab, we grow a nonlinear crystal, we take it and do basic test. After that, when doing application studies, we put it on a goniometer, we rotate the crystal, we pass the IR beam, and we study the generated second harmonic output. It will be maximum at particular angle, it will be vanishing at some point. Again, it will come at maximum. So we have to take the crystal, mount the crystal along the optic axis to generate the maximized output. So this is one of my old papers published in the year 1914. It is about second harmonic generation output in L-alanine crystal. It is organic material. So you could see at the top, the L-alanine crystal. And here you could see two graphs, which I practically did it during my postdoctoral research at Busan National University, South Korea. So here, the left is the angle tuning figure. So you could see the angle is varied from 0 to 10 degrees. Such a small rotation. So it could generate small rotations when mounted with a goniometer and a microcontroller assembly. And the black dot shows the theoretical output and red shows the experimental output obtained for the external angle tuning. Basically, the second harmonic generation intensity is represented in y-axis, and it is normally a sync hyperbolic curve, right? So the right side is the wavelength tuning, the left is the angle tuning, right side is the birefringent phase matching. So when you tune the wavelength from 800 to 1200 nanometer, you could see the energy is maximized somewhere around 1060, right? So here it is the birefringent phase matching. I did both the phase matching for my L-alanine sample. So next, coming to this, another application is difference frequency generation. So what is difference frequency generation? It is again an application of a second order nonlinear effect. You could see the green is nonlinear medium. Omega 1 and omega 2 are the energies or frequencies of the input wavelength, and you are going to generate a new frequency, new color, omega 3, with whose energies will be the differences of the input waves. In other words, how can I say, you are going to mix two beams, say red and yellow color, you are going to generate a new color like violet, right, or purple. So what will be this happening inside? You could see the energy level diagram. The black represents the ground state and the red dot represents the excited state. You are going to send frequency of two waves, signal and idler beams. Here actually it's represented as a single wave. So here you will be getting the difference of two waves. Omega 2 and omega 3 are the sub-virtual levels, you can say. So on returning, you could generate this signal and idler beams. At lab, we'll be pausing a signal beam and idler beam. Signal is visible wavelength 400 to 700 nanometer, and idler is IR waves. It will be tunable IR by using optical parametric oscillator or any tunable IR source. You could generate the frequencies of mid-IR sources with the available laser field. And omega 3 output, we will get pump single wavelength along with the input wavelength. So how you could avoid input wavelength? By using certain color filters for cutting the input wavelength, you can practically generate the output wavelength. So this difference frequency mixing can be done in two possible ways. The other one is optical rectification process. This is yet another DFG, difference frequency generation. Here you are going to use femtosecond laser pulses. You could see how accumulated the laser pulses, the broad bandwidth. So it is going to fall on a nonlinear crystal. You are going to generate picosecond or terahertz laser pulses. So terahertz, coming to the terahertz frequency, some of you might be heard about this terahertz rays, and all of you are familiar with the applications of terahertz. So what is basically a terahertz frequency? It is to the power of 10 power 12 hertz. In other words, it could be equal to 300 micrometer wavelength, and the energy of the terahertz waves are order of few milli electron volts. That is approximately 4 milli electron volts. Terahertz spectroscopy. So it founds a variety of applications with the different materials. What are the basic properties of terahertz waves? These waves have the ability to penetrate on packing materials such as paper, cardboard, plastic, polymers, everything it can penetrate. Some PMMA polymer can stop terahertz rays, and it is a basically non-ionizing radiation, and it has got different spectroscopic applications. This particular slide shows about the energy spectrum of gamma ray to high energy to radio waves. So where lies the terahertz waves? You could see a visible ray that is written on photonics, and here you have see infrared rays and microwave on the left extreme. So the terahertz gap, the terahertz frequency range basically lies between infrared and microwave of the total electromagnetic spectrum, right? So you could see 300 gigahertz to 30 gigahertz or 1 terahertz, right? So what are the basic applications I can show you here? Coming to this, you should know what are the fundamental properties of terahertz. So if you know the properties, then we can decide over the idea of applications, how it will go. So basically the frequency starts from 100 gigahertz. The terahertz gap starts between 100 gigahertz to 10 terahertz. It is the acceptable wavelength range of International Telecommunication Union, but nowadays people are going beyond 30 terahertz, right? So the wavelength falls between 3 millimeter to 30 micrometer. It penetrates to most of the insulating dielectric materials, and terahertz waves are absorbed by water and polar molecules. It is totally reflected by metal surfaces, and basically it is non-ionizing radiation. So it has less health hazards when compared with X-rays, and it could be a replacement for X-rays. So this particular slide gives an idea about what applications they are being used with. You can see the bioimaging of leaflet molecules. You could see the arteries and veins of the molecules of leaves, and it is being in the medical diagnosis field of tooth decay. One could see the root canal filling and tooth decays with the help of terahertz rays. And in terabyte communications, you are using terahertz waves, that is this much frequency waves, and you are using it for manual inspection. You could see a man passed with the terahertz beam. You could see a gun is being hidden with his stomach abdomen part. And for industrial applications, it has one of the main non-destructive testing applications. You could test the linearity or test the validity of your electronic circuits, miniature circuits by passing terahertz rays. You could check the component whether it has been working or it has been spoiled out. And it is used for packaging applications, whether the food gets deteriorated or the food is in normal, just like pickle packages, packed sealed packages. And one of the highlighted application is explosive detections. Normally we use metal detector bombs to search for bombs. If you pass the terahertz beams, you can, without opening the parcel, you can check it whether there is some explosives, just like RDX, toluene, or any kind of explosives are present. So this waves has again such an importance. Let me see that terahertz generation in organic crystals. So you can ask whether the terahertz generation is possible with any medium. Again, there is a stringent condition. You can obtain this terahertz generation only with a material medium that shows second harmonic generation. That is, materials should possess lack of inversion symmetry. It should be non-centrosymmetric material, in other words, simple words, right? So what are the material requirements? The crystal or a medium should have high second order nonlinear coefficient. So in order to obtain second order nonlinear coefficient, the material should be a non-centrosymmetric material. You know, centrosymmetric material example is benzene molecule. C6H6, it is isotropic material. Whereas these are present in the medium should be anisotropy medium. So at least the D coefficient of the evaluated material should be greater than 20 picometer per volt, and it should possess high electro-optic coefficient, right? And there should be a pi conjugation structure. So all basic chemists know what is a pi conjugation structure. So there should be a large delocalization. That is, the mobility of electron should be high, such as crystal structures are always preferred for obtaining parallax emitters. Polar space groups with non-centrosymmetric structures is again I discussed this condition previously. It should possess large damage threshold to meet fast laser pulses. So what are the device requirements? The material should be highly transmitting in UV visible near infrared range. That is, the transparency range should be very broad. And it should possess a desired phase matching angle. That is the optical axis. It should be cut and fabricated along the optical axis direction. The surface roughness of the crystal should be less than 50 nanometer for commercial applications or for commercial. This is one of the basic requirement. The surface roughness should be less. So you have to polish the crystal to get a smooth output. Surface flatness of the crystal, it's tested with helium neon laser. So surface flatness should be present. The crystal should not be just like having a round or spherical structure, which limits the device applications. The dislocation density, that is the uniformity of the crystal. The crystal should be homogeneous, free from any defects. The dislocation density should be the order of 10 power 5. So you can test this with etching studies. Laser damage threshold should be the order of gigawatt per centimeter square. And efficiency, practically the efficiency, at least it should be generate 25% output. It could be used for device applications. Steps involved. So how to, if you are new to the particular research field, so what are the basic idea I am giving on this layout? So molecular engineering concepts by using DFT theory or Monte Carlo simulations are available to predict the organic structures with non-centrosymmetry requirements. There are large thousands of literatures are available for DFT studies, which shows high D coefficient molecules. So theoretically, you can predict that this crystal structure can generate a higher nonlinear coefficient, which will in turn generate the higher DFG or second harmonic generation efficiency. So you should go for such a literatures to obtain new predicted structures. So after getting this, you can go for crystal engineering or concept of synthesis and purification. So you know now a new crystal structure which could generate a high NLO coefficient. So what is the next step? You could go for practical, how to synthesize the particular material. Say you are going to obtain AB molecule. You can take A and B, mix it together, put under some heating or any other process, synthesize it, and purification is yet another to achieve a good crystal. So synthesis and purification is the next part, and crystal engineering or crystal growth is the third step. So after getting raw material, now what should I do? I should grow it into a beautiful crystal. So depending on, there are a lot of methods of doing a crystal growth. Most of you are familiar with solution growth. That is the very simplest and very fundamental process anyone can learn at the home level. So solution growth, from that you have different methods: solvent evaporation, slow cooling, and other transportation methods are there. Gel growth are there. So based on the material vapor pressure, melting point, and other thermal studies, you could do some preliminary screening for your raw material. Any raw material cannot be used for solution growth, or any material cannot be grown for melt growth or Czochralski growth. There are some fundamental basic technical points with that. For example, if material has a melting point of 700 or 1000 degrees C, you cannot grow for low temperature solution growth. And if a material decomposes on melting, you cannot grow for melt growth, right? So there are some stringent criteria for doing crystal growth. So based on that, after growing a beautiful crystal, you have to characterize for its fundamental properties, whether I can put it into application or I can do it at only lab level. So what are the characterization part? You have two major categories. One is the physico-chemical studies based on the present crystal structure. So whenever you grow a crystal, you want to test it. So first I will go for a screening structure like X-ray studies. I can go for a Laue method, whether I want to obtain a single crystal, whether my sample is a single crystal, I can go for law-based path studies, or I can go for single crystal XRD. It is a bit costly, as most of you will know this charges. So after that, I can go for thermal analysis to study the melting point of the material. If it is a new material, I can go for TG analysis, weight loss studies, and other prelim testings. Hardness of the material is at another. So it should be sustainable to mechanical damage as we go for cutting and polishing and all. Right. So the other part is the device characterization, which is basically done with help of lasers. NdAg lasers or helium neon lasers, they are used for testing the crystal samples. So here I'll show some of my grown crystals as in the part of the Women Scientist project, which I obtained from DST. So here is the crystal growth of BNTC molecule. So this work is being carried with the help of collaboration at Sastra, University Tanjavur. So here you could see the solution growth carried out by me at this for this molecule BNTC. So what is something new about this molecule? N-bis 4-nitrophenyl 1R2R diaminocyclohexane. So this particular molecule is a chiral compound. You know, basic chemistry, you can understand what is a chiral compound. So most of the chiral compounds are very NLV active. They possess large D coefficient. So I have chosen this molecule for my studies of terahertz generation. So B shows the molecules. I have tried it with the different solvent ratios by using N-ethyl acetate and N-hexane mixed solvents. The third figure shows the biggest crystal obtained from this particular molecule done by solution growth method. And this is the second crystal grown by me. So this molecule is called DAT2. It is a big molecule. And you may wonder why I'm choosing big molecules instead of going KDP or any basic crystals. So organic molecules, when you consider, basically there is a concept called pi conjugation length. If the molecule's chain length alternates single and double bonds, right? So that structure goes on increasing. The pi conjugation will promote more mobility of the electron, thereby enhancing the D coefficient or terahertz efficiency. So I am looking for bulky structures. And here, this is the third crystal grown by me. Actually, these crystals are monoclinic in structure. They are a bit little difficult to grow into a three-dimensional structure. Monoclinic means you can basically get needle type of crystals. The A-axis is comparatively slow growth rate when compared with the B and C axis. So you could see some rectangular type of crystal obtained in the second figure, right side of the slide. So another molecule is OHMQ. This is a hydroquinone derivative group. The name is very big. You could see the chemical structure and the crystal structure in this particular slide. And you could see the name of the compounds which I have discussed here. So coming to the next slide. So this is the basic experimental setup which is used for terahertz generation. You could see femtosecond oscillator or the titanium sapphire laser. And you could see the refracting lenses and electro-optic plate or the Olsztyn prism and intermediate stages. And you could see two parabolic mirrors PM1 and PM2. And the sample mount between here, the crystal is placed before the parabolic mirrors. Parabolic mirrors are reflected for the terahertzing waves. And you could see a detector, which is based on electro-optic sampling method. And the interface is connected to a computer, right? So you could see what are the components, intermediate components present here. This work is carried out at University of Hyderabad with the help of Professor Anil Chaudhary for carrying this for doing this terahertz generation. So this is one of my paper published in the year 2020. It shows the transparency range, as I earlier discussed. The material should have wide transparency range in the visible and near IR. Otherwise, the waves, generated waves, could be absorbed by the medium depending on this range. You could see the BNTC crystal here and the femtosecond pulse and the generated terahertz pulse. So I could see, I could present the graphs here. So here you can see the frequency generated range. It is good between 0 and 1.2. It is showing broad transparency of the terahertz waves. Then you have smaller minor absorptions due to the nature of the BNTC molecule. So this particular transparency range in which BNTC shows good transparency, it could be used for explosion of detectives. Most of the detectives have absorption between 0.1 to 3 terahertz. So this molecule could be used for direction of explosives. And here you could see the delay amplitude, the femtosecond terahertz amplitude, and here the laser power. It shows the order of 10 power minus 4 electron volt, the amplitude of the generated terahertz waves. So I am going to compare my crystal with other organic crystals. So you could see the transmitted range here, the terahertz range generated and the terahertz peak amplitude. So BNDC I have highlighted in red, and you could see in order to compare, you should use the same laser source and the same conditions. The last three are using titanium sapphire laser source. The generated terahertz range is given, and you could see the others are showing feeble amplitude 10 power minus 5, and here it is showing 10 power minus 4 amplitude, which is good compared with the other ground crystals in the other publications. Next one is the quasi-phase matching devices. So this is yet another application of NLO, second order NLO effect. So what is quasi-phase matching? As I earlier discussed, there are different methods of achieving phase matching for second harmonic generation. Birefringence phase matching, angle tuning, and temperature tuning. So this particular technique is used for ferroelectric crystals such as lithium niobate, potassium tantalate, etc. So here, when you take a ferroelectric crystals, everybody knows there are presence of ferroelectric domains inside the crystal. You are going to cut the crystal, polish the crystal, and pull it in order to get a ferroelectric domain alignment. So if the domains are randomly oriented, you could get less SHG, less second harmonic generation efficiency. So if the domains are going to present in the same direction, then you could achieve the more second harmonic efficiency. So here I am going to show how the crystal medium interacts with the fundamental wave. What is LC's coherence length? That is physical dimension of the crystal is different from coherence length. Moreover, say if the crystal is going to be 1 centimeter crystal, I am going to pass a laser wave. The generated second harmonic sometimes may remain inside the crystal. It may not come outside. It could be green signal could be seen inside the crystal. It may not come outside of the crystal. So the coherence length remains a small part of the total length of the crystal. So every LC, every coherence length gets repeated. The second harmonic, I could see the, everyone could see 3 types of waves passing through it. The red shows the ideal case. For example, if I am going to give 5 millijoule of omega fundamental wavelength, I could able to get the 100% of conversion of 5 millijoule of omega into the second harmonic wave. So that is the ideal case. In this black, which is like a sinusoidal wave, so it could be the ideal mismatch wave. That is, if the crystal has some defects inside or some distortions, the generated second harmonic remains inside the crystal. So for every coherence length, it maximizes, and after that, the second harmonic wave gets decays, it goes to 0. So the generated output cannot be still visible, even though there is a green flash from the crystal. So the figure B, intermediate figure, shows the concept of quasi-phase matching, which could be achieved by aligning the ferroelectric domains in such a type of crystals. So coming to the quasi-phase matching devices and applications of lithium niobate, here I am going to highlight the applications of lithium niobate. So this research is being carried out at the collaboration of Shastra University with Dr. Krishnamurthy Pandian, School of ECE at Shastra University. So here, all laser pointers are used in the market, right? Different colors of laser pointers. Basically, if you go inside the construction of the laser pointer inside, you could see a semiconductor wafer, that is a diode pumped structure, which is shown in the figure below. So this diode pumped wafer, semiconductor wafer present inside generates the laser by means of the lasing process. But when you go for the green laser pointer, it is normally not available with the semiconductor structures. You could go for a big structure. It uses the neodymium yttrium vanadate, that is NLO crystal, for generating green color laser, right? So this shows the typical green diode pumped solid state laser with multiple crystal assembly. That is a fundamental crystal structure. Neodymium yttrium vanadate should be there, and a second harmonic crystal, KTP, potassium titanyl phosphate, or KDP, should be present inside for generating green color. But here, in order to minimize the structure, because laser pointers are very portable, you can carry it with the hand. So in order to achieve such a structure, you can replace it with a periodically poured lithium niobate. That is, you can grow the lithium niobate crystal or buy it commercially. You can pull this crystal, make the alignment of ferroelectric domains and use it for applications. So this is application of lithium niobate in the recent technologies. So this is first figure shows the heads-up display used in cars in foreign countries. So I soon it will be available in Indian market too. So here heads-up display means there will be a projector on the top side of your car, and if you are driving on the rear side, you could see the GPS information on your car screen instead of the small screen present in your front. And the right side shows the pico projectors available by using the PPLN samples. So pico projectors, when you open inside the projector, you could see the lithium niobate wafers present inside. And the third, this structure will be like this, the crystal structure followed by the PPLN, right? So RGB, primary colors are red, green, and blue. RGB color could be generated with a single crystal structure, that is PPLN, right? And then this is yet another of the lithium niobate. One of the interesting properties of this material is very good transparency range in the IR region, right? So when long time back, there is a missile that it be hitting the warfare aircraft. Some aircraft has been destroyed in the country of Uzbekistan, I guess, right? So in order to avoid such a big calamity or a big destroy, so what we can do is, in designing the aircraft, we can place a IR jammer made up of periodic lithium niobate crystal, which has high good transparency IR range. So whenever some terrorists or somebody enemies are attacking the warcraft or airplanes with a missile, so this missile normally will have a IR tipping nose. A nose means some IR detector. This will detect the warcrafts in the region of sky, and normally they will go and hit which contains the IR maximum intensity. So if you place a IR jam as a countermeasure from the airplane, it will confuse the electronic nose of the missile, and the missile path gets deviated and it will fall into some sea or some other waste area, right? So what are the benefits of quasi-phase matching devices? So materials having low birefringence, that is low anisotropic materials such as lithium niobate, tantalate, you can achieve good phase matching with this concept. And materials in the desirable frequency range, it could be used for applications without wasting them. And you can assess the large nonlinear coefficient in particular direction. All this D3, D13, it is based on the directional property of the crystal, right? Next, coming to this fabrication of quasi-phase matching devices, as I told, you obtain a ferroelectric crystal or as a wafer commercially purchased from a company. You can use this DC electric pooling method. You align the ferroelectric domains in the crystal. Randomly aligned domains could be arranged perfectly. So by polling the crystal, you could be able to see a polled crystal sample and the polling facility available at Shastra University. So the domains could be properly aligned for the second harmonic generation process. And this is one of my collaborative publications with the Shastra group. And this is the coming yet another technology, integrated photonic devices, that is lab on a chip, single chip periodically polled lithium niobate wafer could perform 2 or 3 optic modulation process, and you are able to get a small circuitry function with the same crystal sample. And coming to the conclusions, organic crystals with the pi conjugation bridges are very interesting candidates for terahertz applications. The well-known material is dashed, and the recently grown materials are benzyl, nitromethylene, aniline, BNA, etc. BNDC is the crystal that has been done by me for the DST project. And there, I obtained a terahertz efficiency, which is the order about 10 power minus 4 volt amplitude. And QPM devices based on lithium niobate can be a potential candidate for various applications such as heads-up display, frequency converter, broadband sources. And I acknowledge my mentor, Professor D. Sasthikumar, Department of Physics, NIT Tiruchirappalli, for giving me permission to grant out the studies. And I thank Dr. Anandan, Department of Chemistry, NIT Tiruchirappalli, for providing lab for synthesis. and offering synthesis facilities. I thank Dr. Philip Anthony, Sastra University, for collaborating research with the BNDC molecule. I thank Dr. Suman Bagachi, RR CAT, and Dr. Anil Chaudhary, Arkham, University of Hyderabad, for tendering help to carry out Taragat studies. Finally, I thank DST for offering me this grant, and I thank all the research scholars and my dear students who are attending this meeting. Thank you, organizers, for giving me this wonderful opportunity to discuss my research ideas with you. Thank you, one and all.
Thank you, ma'am. Dear friends, if anyone have any questions or doubts, you may clarify them now.
Any questions, dear students?
Good afternoon, ma'am.
Yes.
How many heads is terahertz?
10 per 12, ma. 10 per 12 heads.
Thank you, ma'am.
Yes. Welcome. Yes, no questions?
You can also share your doubts in the chat box.
Yes.
Anyone else? Thank you so much, ma'am. I ask Ms. S. Kavipriya, second MSc Physics, to propose vote of thanks.
Good evening to one and all present here. First and foremost, I extend my gratitude thank our Almighty for making this day a grand success. Leaders become great not because of their power, but because of their ability to empower others. First of all, I am happy to extend my gratitude to our Secretary, Reverend Mother C. Noel Rani, FSAG, who gave permission to conduct this event. And also, we thank our presence and blessing. Thank you, Mother. Leadership is the capacity to translate vision into reality, dare to lead. I also extend my sincere thanks to our principal, Reverend Sister Dr. E. Glita Sumangali, FSAG, Department of Physics, whose presence made this event meaningful. Thank you, Sister. A leader is one who demonstrates what is possible. I am proud to give special thanks to our Vice Principal, Reverend Sister A. John Diana, FSAG. Thank you, Sister. To succeed, you need to find something to hold on to, something to motivate you, something to inspire you. I am happy to thank our honorable research person, Dr. S. Puma Devi, DST, Women Scientist, Department of Physics, NIT, Tiruchirappalli. Thank you, ma'am. Talent means nothing, while experience occurred in humility and with hard work means everything. It is my pleasure thanks our honorable research person, Dr. K. Seduraman, Associate Professor, Department of Material Science, Central University of Tamil Nadu, Tiruvarur. Thank you, sir. Knowledge is having the right answer. Intelligence is asking the right question. Here, I extend my gratitude to our honorable research person, Dr. S.K. Das, Head of Professor, School of Physics, Gangahar, Mehar University, Sambalpur, Odisha. Thank you, sir. I extend my graceful thanks to all the faculty members and supportive staff members who have made huge effort to become the webinar. I also extend my heartfelt gratitude to all staff members, research scholars, and students from various colleges who have participated in this webinar. Once again, I thank you everyone for your cooperation in attending today's webinar with full of spirit and enthusiasm. Thank you.
Dear participants, we will send the feedback link to WhatsApp group. You may share your opinion. Thank you all. You may leave the meeting. Thank